Good morning. Let's get started. So it's a pleasure to welcome you to the second day and the opening ceremony of the ICTP-SAIFR 12th Anniversary Symposium. So thank you for coming, and we need to give also a special thank to Professor Vahan Agopian, who is here. Who is Secretary of Science and Technology and Innovation for the state of São Paulo. And so as you can see, we have many speakers this morning, and they will talk about the institution they represent, starting with Maysa Furlan, who is vice-rector of the São Paulo State University, Antonio Zago, who is president of the FAPESP, São Paulo State Research Funding Agency, Atish Dabholkar, who is director of the Abdus Salam International Center for Theoretical Physics, the father of the main ICTP. Ricardo Matheus, who is director of the local institution IFT-UNESP. Nathan Berkovits, the director of ICTP-SAIFR. We have Rosario Rosenfeld here, who is vice director of ICTP-SAIFR. Pedro Vieira, who is the coordinator of the relationship between Perimeter and ICTP-SAIFR. And then we have Lucas David, who is outreach coordinator, and Ana Luisa, who is coming. And a special thank also to Professor Edson Botelho, who is Dean of, here sitting in the front line, Dean of Research of the São Paulo State University. So, without further ado, since we have many talks, let's get started.
Bem, bom dia a todos. Good morning to all. É melhor acho que todos sentarem aqui agora, não, Neita? It's better to move to the auditorium here. Yeah? To see the presentation, no? Can go there. Ok. Thank you very much to all. Eu vou falar em português, o Neita disse para eu falar em português, um pouquinho sobre a nossa universidade. Não está funcionando ali, né? Oh, acho que não está adequado aqui. Oh, ok. Esta é a Unesp. A Unesp é uma jovem universidade, tem 48 anos, e é uma universidade que tem um modelo bastante distinto. Ela está espalhada por todo o estado de São Paulo, né? Então, vocês veem, se nós traçarmos um círculo aí de 100 quilômetros, a Unesp tem um campus. Ela está em 24 cidades e tem 34 unidades universitárias. A Unesp em números, então nós temos 34 unidades universitárias em 24 campos, temos um pouco mais de 50 mil estudantes, quase 40 mil de graduação e 14 mil de pós-graduação. 98% dos seus docentes são contratados em RD&DP. Tem também 136 diferentes cursos e 149 cursos de mestrado na pós-graduação e 117 cursos de doutorado. Forma 5.000 alunos em nível de graduação por ano, 2.000 alunos em nível de pós-graduação e 1.000 doutores por ano. Está bem em português, tá? Quando falamos um pouquinho de ranking, esta é a posição da Unesp, nos principais rankings acadêmicos, né, e no Global Ranks ela está ali entre a top 3%. E na América do Sul é a 10ª universidade, e no Brasil a 5ª universidade. Nós temos aqui, olha, vários institutos de pesquisa, inclui aqui, né, o Instituto de Física Teórica, e também, claro, o ICTP, que é seu grande programa hoje aqui internacional. E nesses outros institutos de pesquisa, nós chamamos de unidades complementares. Então, eles desenvolvem aí pesquisa de altíssimo nível, com programas de pós-graduação também bastante qualificados em várias e diferentes áreas do conhecimento. Claro, a universidade ela tem aí um impacto social bastante grande, tem um sistema de inclusão muito sólido, incluiu mesmo antes, desde 2014, mesmo antes de 2018, quando a lei prevaleceu, e ela, pela sua dinâmica, e pela sua infraestrutura, ela tem um impacto tremendo no estado de São Paulo, especialmente no interior do estado de São Paulo. Ela tem, então, uma interação, especialmente pela sua distribuição, com vários setores da sociedade e contribui aí com a comunidade e com o seu conhecimento gerado, que é realmente bastante qualificado. Então, aqui, ela contribui ali nas economias locais, emprega muitas pessoas, apresenta hoje uma atividade de inovação bastante grande, desde os alunos até os seus docentes, e nós temos hoje 50 empresas júniores atuando em todo o estado de São Paulo. Temos aí um conglomerado de clínicas, hospitais na área de saúde. Então, temos hoje 3 hospitais universitários, um grande hospital que é mantido pela secretaria e não mais pela universidade, e temos também 3 faculdades de odontologia que trazem aí, claro, um atendimento muito importante para todo o estado de São Paulo, porque essas unidades todas, e inclui aí fisioterapia e outras carreiras, elas estão aí espalhadas por todo o estado de São Paulo, e nós temos o Instituto de Confúcio, que é um dos maiores do mundo, e mais que isso, ele foi considerado aí por 3 vezes aquele que forma o maior número de estudantes aprendendo mandarim. Eu gostaria de passar aqui, eu vou passar rápido aqui também, e chegar aqui. Nós temos aí programas de pós-graduação de excelência, e nós incluímos aqui o programa de pós-graduação em física, e outros programas ali que também são de excelência, tem a nota máxima na avaliação da CAPES, e eu aqui gostaria de dizer que a universidade é aquela que é a segunda em maior número de programas de pós-graduação no país. Então, a universidade é a segunda, e em termos de pós-graduação também qualificadas, ela tem avançado muito. A primeira é a Universidade de São Paulo, e nós temos aí também um grande sistema de pesquisa, ancorado pelas suas unidades universitárias, pelos seus centros de pesquisa, e uma dessas contribuições, Neita, é aqui o Instituto de Física Teórica, que contribui assim, de maneira fenomenal para a qualificação do conhecimento na nossa universidade. Então, aqui nós temos aí vários dados que corroboram essa qualificação. Hoje, a universidade ela representa, em termos de produção científica, 8% do total da produção científica no país. As 3 universidades públicas do estado de São Paulo também representam aí quase 50%, e nós temos também aqui 3 universidades federais que compõem o conglomerado de ensino superior do estado de São Paulo. Aqui nós temos várias áreas de pesquisa, com a contribuição forte ali da física, lá 9,7%, e nós temos realmente a contribuição da área de saúde com muita qualidade, bastante decisiva, e várias outras áreas que mostram a excelência do conhecimento gerado pela nossa universidade. Temos aí aumentado sobremaneira o nível de colaboração internacional, o ICTP ele representa também esta porcentagem bastante, eu acho que ela tem crescido muito aí nos últimos tempos, não só em número, e aqui vocês podem ter ideia dos nossos parceiros internacionais, né, e do número de parcerias que os nossos docentes e pesquisadores exercem hoje nas unidades universitárias e nos centros de pesquisa, mas também na qualidade da pesquisa gerada. Nós temos aí algumas estratégias de pesquisa, claro, alguns temas importantes, né, e um dos temas, e esses temas, muitas vezes, estão ligados aos objetivos do desenvolvimento sustentável, né? Então, aqui nós temos vários temas que compõem hoje um grande projeto internacional da universidade, né? Então, a internacionalização realmente da universidade, ela hoje é um processo transformador para nós, ele é muito importante, e com isso, Neita, o ICTP, né, para essa universidade é primordial, né? Nós temos aí algumas premissas que nós desenvolvemos, né, com apoio, com suporte, e muitas vezes, né, privilegiando o nosso plano de desenvolvimento internacional, e aqui está colocado, né, e eu acho que o ICTP ele participa dessas premissas, né, com bastante ênfase, baseado nos 3 pilares, e que a universidade tem avançado aí resultados fenomenais, né? A internacionalização, ela tem aí algumas premissas: a internacionalização em casa, o reconhecimento das atividades, das carreiras. Então, nós temos privilegiado o intercâmbio não só de docentes como de estudantes, mas também do nosso corpo administrativo, né? Nós temos aí algumas estratégias que estão conglomeradas ali, mas, dentre elas, né, nós privilegiamos parceiros em algumas temáticas de pesquisa e, claro, a mobilidade e a atração também de pesquisadores internacionais. Para nós, isso é muito importante. Nós temos trabalhado muito com isso no nosso plano de desenvolvimento institucional, né, e foi uma nessa premissa, a contrapartida da universidade, uma das contrapartidas da universidade ao ICTP é exatamente, né, esse trânsito de pesquisadores do exterior, de grandes centros, para contribuir aqui para a nossa universidade, né? E aqui nós temos também, claro, como prioridade as estratégias com os parceiros, e temos avançado sobremaneira nessa premissa, e, mais que isso, claro, tem também as estratégias transversais, né, que movem todo esse plano de desenvolvimento institucional, e que está mostrado ali da nossa universidade. Nós temos um grande projeto aí, que é o projeto CAPS-Print, né, que traz como tema, foi um projeto que foi aprovado na gestão anterior, submetido à CAPES, é o segundo projeto que tem ali a maior verba daqueles aprovados, né, no Brasil. Ele foi baseado nos Objetivos do Desenvolvimento Sustentável, e, a partir daí, nós criamos, né, um ambiente de pesquisa bastante forte e muito ligado hoje a essas temáticas, né? E, no desenvolver desse projeto, nós criamos também as Global Alliances, as alianças globais, que hoje estão sendo desenvolvidas em diferentes temáticas, com grandes universidades e qualificadas do mundo, né? Aqui está o ICTP e sua contribuição aí nas publicações científicas da nossa universidade. Ele tem contribuído sobremaneira. Aqui estão os coautores, autores, né, de artigos que prezam aí realmente o conhecimento qualificado gerado por esse programa. Está aqui a Unesp e a ICTP nas grandes áreas que vocês têm desenvolvido, a sua porcentagem, e nós vemos aqui a qualidade, né, a expansão dos temas, né, e, mais que isso, nós temos aqui a visão, né, do que significa o ICTP para essa universidade, para o mundo, né, e para o grupo todo de pesquisa que está sendo envolvido, que está envolvido aqui. Eu tinha trazido, essa não era a apresentação final, eu tinha trazido todos os dados da FAPESP, acho que o Edson tinha enviado, né, Edson? Mas eu gostaria de dizer que hoje na FAPESP nós temos também aí vários. Eu acho que a participação dos nossos docentes em vários programas, hoje nós temos 35 temáticos, nós tínhamos todos os valores levantados do ICTP, essa não era a última, desculpa, né? E mais que isso, né, temos participado ativamente, e eu gostaria aqui, na presença do professor Zago e do professor Varran, dizer que nós temos dado passos fenomenais agora, com essa nova visão da FAPESP de montar centros, né, importantes e necessários. Então, tem aí o do supercomputador, que reúne, que mais do que ela trazer nova infraestrutura de pesquisa para a nossa universidade, ela também congrega pesquisadores, né, das universidades paulistas. Esse projeto é um projeto que vai ancorar, eu acho que daqui para frente, todos os planos das universidades. Então, eu acho que já foi aprovado, eu acho que já estamos aí em fase, né, de estruturação desse novo programa. O professor Zago colocou na reunião preliminar que alguns programas institucionais, né, grandes, que vão servir todas as universidades, eles estão aí na mira da FAPESP. Então, nós estamos saindo hoje de um patamar e caminhando para um patamar muito mais amplo, um patamar que traz aí alicerce, um patamar que vai elevar a pesquisa do Estado de São Paulo num nível assim, que todos nós estamos bastante satisfeitos. Então, professor Zago, muito obrigada aí por esse rumo da FAPESP, professor Varran. E eu gostaria que, de finalizar, e sempre finalizo com essas duas questões que eu acho fundamentais no Estado de São Paulo, para o avanço da ciência no Estado de São Paulo. Quer dizer, grupos que trazem aí a perspectiva, né, de programas como o ICTP, aqui agora, que nós alojamos, né, no nosso Instituto de Física Teórica, o ICTP da América do Sul, e outros grupos nossos que trabalham. Nós temos hoje aí um CEPID que vai avançar, né, para ter um braço. Eu estava conversando com o professor Varran, né, do Instituto Fraunhofer, da Alemanha. Então, hoje nós temos estruturas aí, e vamos somar, né, professor Zago, aí, ao CNRS, ao Instituto Pasteur, né, trazendo aí tecnologia e novas possibilidades para as nossas universidades paulistas. Mas, mais que tudo isso que eu mostrei aqui hoje, eu avanço e eu estendo aqui as nossas co-irmãs, USP, Unicamp, estendo para as nossas irmãs, né, federais que estão no Estado de São Paulo. Eu acho que tem duas questões que são fundamentais. Uma é a autonomia universitária, né? Então, é uma luta que nós temos que estar sempre atentos. Ela é frágil no Estado de São Paulo, mas ela é importante e ela é decisiva para que nós possamos avançar e para que e para este cenário que todas as universidades, as co-irmãs, apresentam hoje em termos de conhecimento e oferecimento de formação de recursos humanos. E a outra é a FAPESP, né? Eu acho que a criação da FAPESP ela é responsável aí, por todo o desenvolvimento de pesquisa no Estado de São Paulo. Então, eu acho que nós temos aqui duas joias, né, que nós temos que brindar e defender a todo momento. Então, muito obrigada, Neita. Muito obrigada a todos.
Desligou. Ele não vai ficar traduzindo. Não. Okay, my friends, good morning. I'm very glad to participate in the opening of the symposium that commemorates the 12th anniversary of SAIFR, a research center linked to the ICTP in Trieste. I wish to compliment the directors of SAIFR and the foresight of those who established this center in 2011. I wish also to reaffirm to the director of ICTP, Professor Atish Dabholkar, our determination to strongly support SAIFR, to expand its annual schedule of meetings and seminars, as well as to create new formats to bring together scientists to discuss and propose solutions to subjects that are central to the life of this center. Together with Nathan Berkovits and the rector of the University UNESP, we have been discussing ways to strengthen the program of SAIFR and make it the most important hub of physics in Latin America. I think we should be very clear what is our objective. It's to make this center the most important hub for physics in Latin America. This initiative is independent, but synchronous with the recent decision of FAPESP, Board of Trustees, to implement an ambitious program of quantum science and technology, which we are launching this month. We are convinced that the two movements by FAPESP will create a thriving environment for contemporary research in physics in the state of São Paulo. The two initiatives are complemented by the board's decision to increase the investments in fellowships, to boost and increment the opportunities for younger researchers in these fields, as well as creating opportunities to bring researchers from abroad, either temporarily or permanently, as illustrated by our strategy of young investigators, for which FAPESP will open immediately a specific call for quantum science. Also, there is a call open at the moment to bring to São Paulo postdoctoral fellows in all areas of knowledge, including physics, in a joint initiative with TUAS that is attracting a large number of candidates. Finally, SAIFR fits the model of international cooperation that FAPESP is encouraging and sponsoring, such as the Institut Pasteur and the CNRS International Center at USP. The objective is to have in São Paulo a dozen of centers that share resources and are linked to the networks of prestigious international research institutions, such as ICTP, Pasteur, CNRS, Fraunhofer, Max Planck, Fermilab, and ICGB. I wish thus thank the directors of SAIFR, the director of ICTP, the director of the Institute of Física Teórica, IFT, the UNESP rector and vice-rector who is here with us, and the Institute Principia for promoting this symposium. Thank you for your attention. Okay.
Ok, parliamo in italiano. Okay. So, no, so first of all, it's a great pleasure for me to be here. Thank you very much for this invitation. I would like to start out by saying that since ICTP has been involved since the foundation of ICTP-SAIFR, it's a very proud moment for ICTP that this initiative, which started 12 years ago, has flourished and has really developed so nicely. And I want to thank Nathan for all his dedication and also all the colleagues who worked with him for making this a reality. But also I would like to thank the rectors of UNESP and FAPESP and IFT for hosting this and supporting it. And I'm very happy to hear that what the future holds is even brighter than what we have done in the last 12 years. So as it happens, this is also the 60th anniversary of ICTP this year, 2024. So it's just a perfect occasion for us to celebrate the 12th anniversary and the 60th anniversary. And so I would like to tell, I mean, many of you have been to ICTP, many of you have very strong connections with ICTP, but some of you have not. And I would like to give you a quick overview of this ICTP in the context of the 60th anniversary and in the context of the 12-year collaboration that we've had with Brazil. So this is ICTP. It's in a very beautiful location. This is the campus of ICTP right next to the Adriatico guest house. Sorry, Adriatico Sea. And this is, we have our, this is a castle. So it's a very beautiful place. And I will basically, there are three themes I want to talk about. ICTP since 1964, ICTP and Brazil. And of course, I would like to take this is really not just an opportunity to celebrate the past, but we really want to prepare for the future. So how do we imagine ICTP in 2064? And so ICTP is really is a very unique organization, as you know, perhaps one of its kind in the world, founded by Abdus Salam. And it is governed by some tripartite arrangement with the Italian government, International Atomic Energy Agency, and UNESCO. It's a Category 1 center of UNESCO. And the first chairman of our council, scientific council, was Robert Oppenheimer. And I think some of the people here, David Gross and Bill Bialek, they have been on our scientific council. And our fundamental mission is to make advanced science globally available, overcoming the barriers of gender, ethnicity, but quite importantly, I would like to emphasize also geography and economics, because this is what you also must experience, and I come from India. Regional variations also make a huge impact on the career of a person, of what they can do in science. And I think the successful delivery of ICTP rests on these three foundational principles. One is, of course, excellence at the frontiers of science to really maintain our scientific quality, then global inclusion for scientific resources, and international cooperation through science. And I was very happy to hear from the vice-rector and also from Dr. Zago that internationalization is really also the emphasis of your vision for the future, and which I think is the right approach. Brazilian scientific community is at a level that it can really play a leadership role in the region and internationally. So just to give you some very quick numbers, ICTP since 1964, we have hosted and invited close to 200,000 scientists from basically every country around the world. About 30% have been women, about 2/3 are from developing countries, and they are fully funded by ICTP for their scientific visits for 2 months, 2 weeks, or 2 years of different durations. So every year we get about 7,000 scientists and 60 very high-level conferences in a very broad spectrum of research. It, of course, started with theoretical physics, but now we cover quantum information, condensed matter physics, mathematics, climate science, quantitative life sciences. So it has contributed to many scientific breakthroughs, including to 5 Nobel Prizes, and we have partner institutes in these countries. And this is the global impact of ICTP, apart from the activities that take place at, on the Trieste campus. You can see we really have a pretty strong global imprint around the world where we organize conferences, we have affiliated centers, and so on. And the model of ICTP is to really support scientists and to build communities. So I just want to take one example. This is Professor Narayana Adhikari, who is a professor in Nepal. He has successfully created a community of hundreds of researchers in Nepal. But he started as a student at ICTP in 1997. But it's not that after he graduated, he just went back and then ICTP really remained engaged with him throughout his career. He came to ICTP as associate, as senior associate, really throughout his scientific career. And this is really the strength of ICTP, that we have this large community of scientists around the world who are deeply engaged and committed to ICTP. So these are some. Now let me come to the second topic, which is ICTP in Brazil. So these are the scientific visits from Brazil. You can see roughly we have about 300 people visiting from Brazil more recently. So altogether, about 5,000 scientists from Brazilian scientific community have been to ICTP. About 28% are women. In various, we have a broad spectrum of activities. We have associate members. We have this training and research in Italian laboratories, because we are a theory institute, but we also place people doing experimental work in laboratories around STEP. It's a sandwich program, and so on. Affiliates, Electra is a synchrotron facility. So we have had many eminent Brazilian scientists have been recognized for their work through our many prestigious prizes. The ICTP prizes are, you can read the names. I think some of them are sitting here. This is, of course, a photo when their beard was white or black, but, and the Ramanujan Prize. Then there was a ministerial delegation at the G20 meeting when the minister visited together with a group of scientists. And, of course, our partner institute opened in 2012 to bring this unique blend of our high-quality physics and mathematics education closer to scientists in South America. So the idea, of course, is that to really, rather than Argentinian scientists going all the way to Trieste, it's much more, it makes a lot more sense to really build the community within South America. And I'm very happy that SAIFR has been playing this role really exceptionally well. Now, let me come to the final topic, which is the ICTP in 2064. And I like to take this analogy of ICTP is really like a lighthouse for global science. This is a very beautiful lighthouse in Trieste. You can actually see ICTP in the background over there. And that really is the vision for ICTP in the future. And then the question I asked myself when I became the director, that of course, Salam had a certain vision, which was valid in the 60s. So what parts of that vision still are relevant today? And in what way it needs to be modified to take into account the change that has happened around the world? I mean, Brazil and India are no longer the same kind of developing countries that they were in the 60s. So the whole modality of engagement, the way ICTP should engage with the rest of the world has to change. Also, the frontiers of science have moved. I mean, we are no longer looking for the Higgs boson. So that also has to be taken into account. So I myself, I work in a field rather similar to Salam's in black holes and string theory. But institutionally, I think ICTP's spectrum has to be broader. And the way I would put it, I think, and you would all agree with me, I think the role of an international center like ICTP in building scientific communities and creating the culture of science and promoting international cooperation through science, I'm convinced that it is even more valid today than it was in the 60s. If you just look around the world, what is happening, I think science offers a way of really bringing people together. But it should now be more in the nature of equal partnership, because I think we have strong communities around the world. Second point, which I will just quickly go through, is like open science was our fundamental mission. And I think it's clear that in the coming 10 years, open science must include in it, very intrinsically, open access to computing. Sorry, there's a typo. As its mission. And ICTP has been a door opener for initiating and nurturing infrastructures and catalysts for international cooperation through science. For example, this wonderful project, the Sesame Synchrotron Facility in Jordan, which really stands out in the, if you look around the world, what is happening, as a kind of an alternative vision of the future where people can coexist and collaborate rather than go to war with each other. And this role is also equally important, I believe. And I think Brazil could actually play an important role here, being the center for. So let me just quickly tell you a bit about this idea of open science. And with these ideas, I have been discussing. I had the opportunity to discuss with the Brazilian ministry, also with Professor Galvão at the federal level, and possible collaborations with Brazil. And I'm very happy that we can think of similar collaborations now using SAIFR as the nucleus with the São Paulo state. And this, I think, is a very promising idea. I should emphasize that I talked about ICTP in 2064, but you could also ask the question, SAIFR in 2064, how would it look like? And I think ICTP was rather similar to SAIFR in some ways. We had 5 or 6 people to begin with at the time of Salam working in theoretical physics. And now we have grown into many, many different areas. And I don't see why SAIFR cannot follow the same path. If you grow organically with a real clear strategic vision, I'm quite sure, and if there is support from the state, I think it is not, it is certainly within the realm of possibilities that SAIFR becomes what ICTP is. So when the 60th anniversary of SAIFR is celebrated, I hope you would be at the similar level. So just to give you one example where ICTP is beginning to think a little bit differently compared to in the 60s, is that we have initiated this international consortium for scientific computing. It's slowly beginning to take shape. I mean, this is our, of course, this is our ambition, which always exceeds our resources. But there is a large divide. The main argument is that there is really a large divide between the US and even Europe, and certainly with the developing countries, when it comes to artificial intelligence, quantum computing, use of modern algorithms, modern GPUs, whether it is climate modeling, quantum materials, or also nowadays even more abstract topics like algebraic geometry or topology, people are now beginning to use. So 10 years down the line, I mean, I'm myself a paper and pencil kind of a theorist, but it's clear that the science is going to be done very differently 15 years from now. And I really consider it as an obligation for ICTP, if we are committed to open science, to be really offer these opportunities to scientists from the developing country and to look around for resources. And this is what we have been doing. And with that goal, we have successfully signed MOUs with the national agencies in South Africa, with the ministry in Indonesia, with IBM, and this is an example of why it is called a consortium. It's not just an institute in Trieste. So for example, IBM is really keen to support very high-level schools in artificial intelligence and quantum computing, bringing together scientists from around the world, and it could even take place sometimes here. And these are the kinds of ideas that can go in this consortium. There are Swiss supercomputing facility, Cineca, which is the Italian supercomputing facility. They are keen to make computing time available to scientists from the developing world through ICTP. So I think there are many opportunities, and MOU with Brazilian ministry is in the making. And I'm looking forward with Professor Zago that we can do something similar with the, just to give you a final point about, I talked about the international cooperation. Sirius, as you know, is a wonderful fourth-generation machine that exists in Sao Paulo. And I think ICTP has been one of the supporters of this LAMP light sources for Africa, the Americas, Asia, Middle East, and the Pacific project. And I think there are many areas, I have discussed it with you briefly, where we can think of partnership which could be meaningful. So I would say that there are great opportunities for stronger collaboration. This MOU, as I said, is being discussed, consortium, research areas of direct relevance both to Brazil and ICTP, such as climate modeling and quantitative ecology, cooperations around Sirius and synchrotron-related physics in partnership with Electra, and I'm sure we can think of more. So our year of celebration at ICTP, we are, in addition to all the celebration, we'll have 3 major symposia on these very important topics: future of computing, future of climate and energy, and nuclear risks, really getting the top people in the world to deliberate on these very important issues. And these are topics very closely related to the UN, because we are a UN organization, Summit of the Future, which was highlighted by the UN Secretary General. So I think ICTP's role for the as an international hub for science is going to be important in the next 40 years. And I would say that same for ICTP-SAIFR, that it would become even more bigger and influential international hub for science in Latin America. So I will stop here. Thank you.
Okay, so let me start by thanking Nathan for the opportunity to talk a little bit about IFT and congratulate on the anniversary of ICTP. My idea here is to give a little bit of insight on the many institutions involved in this, because people sometimes get confused about who's doing exactly what. And I'll start doing that by telling a little bit about the story of IFT-UNESP, right? So it starts in '52, so it's one of the oldest institutions represented here today, right? And it started with the Léo Ferreira family, right? This is the father, there's 2 sons there, the 2 brothers, and it started as a private institution, right? Which is very uncommon for Brazil. And at first, all the scientific directors of IFT were invited from abroad to try to bootstrap, to start strong on a scientific tradition, right? So you had this initial German phase, these were the directors, right? And then there was a Japanese phase that went up to '61. And then finally, in '61, the first Brazilian director of IFT was elected. It was one of the 2 sons over there. And so this worked as a private institution, but was heavily, of course, funded by the state, especially by FINEP, right, which we heard about yesterday, which helped pay for the salaries of the professors, but the real estate was belonging to this foundation, right? There was a foundation that owned all the real estate where the institute operated, right? From the very start, IFT kept this tradition of being a fairly small institution in terms of number of professors, right? Through time was about 20 professors, right? Plus or more or less, right? But with a fairly sizable footprint in the physical community of Brazil, right? So IFT had direct participation in many landmarks of
milestones of scientific development in the state of São Paulo. So people were involved in the creation of FAPESP, the Brazilian Physical Society, the Brazilian Journal of Physics, which is the biggest Brazilian publication in physics. It started as a journal created by Paulo Leal and then became the Brazilian Journal of Physics afterwards under the direction of Jorge Leal. So, and throughout history, despite having only a few professors, IFT always had representations on the scientific councils of important entities like CNPq, FAPESP, etc. Right? So, despite being fairly small, it maintained constant influence over, and I dare say, positive influence over the development of physics in Brazil. Of course, the 80s were a tough time in Brazil, right? This is the growth of GDP in each decade, 70s, 80s, 90s, and 2000s, right? And you can see that in the 80s, the GDP per capita of Brazil went down, actually. So Brazilians became poorer. That hit hard all financing agencies, and science financing is usually hit harder when that happens, right? And that meant that IFT went through a lot of trouble paying salaries, actually, in the 80s. Right? And that led to a change. So what was one IFT at that point split into two different institutions, right? One, all the graduate program moved into UNESP. The professors were all hired by UNESP. The technical staff, I mean, the administrative staff went all into UNESP, and IFT-UNESP was created, right? The foundation still existed and owned the real estate, right? And these two institutions started at first coexisting, right? But slowly became independent from each other. Nowadays, the IFT Foundation works under this Instituto Principia brand name, right? And we'll be there tomorrow. We'll hear about it. I guess Professor Capelli is here. Tell us a little bit more about these activities. I will follow that track. Right? So IFT-UNESP joined UNESP. Right? I have a few slides talking about the size of UNESP and the state of São Paulo, but Professor Furlan already did a much better job of doing this, so I'll skip these two slides. Right, and talk more about IFT. So these two institutions continue to coexist in the same place, which is where we will be tomorrow, until 2009, right? When finally this campus was built and we moved to the new installations here. So this building, this auditorium. Right? And then that was good because also by moving out, we allowed that real estate over at Pamplona to be dedicated to even other activities, right? So now we have these two fairly independent institutions working and doing their own stuff. And there are a lot of interesting activities happening there too, now that they don't have to use all their space to host us, right? So now, let me say a few numbers, right? So this is the story, a few numbers. Today we have 16 professors, right? Hopefully, we'll have 20 by 2005 because we have 4 permanent positions open this year. These I must thank Professor Furlan, Professor Botelho over there because it's not trivial, right? Politically, it's not trivial to get 4 positions on top of 16 in a university as big as UNESP. That goes to show the continued support for IFT and ICTP. 2 of these positions are directly connected to SAIFR. Right? And so we are about to start selection process for that, trying to attract candidates. Everyone is invited to point good candidates to us. Right? And we have about 70 to 80 students in top grade graduate program. Right? There's this grading of graduate programs in the country. We have the maximum grade now for more than 10 years. Yeah? There are about 200 papers published per year. A good chunk of that is through big experimental collaborations, right? And these are the areas covered by IFT. I mean, there's a lot of different areas, right? And many of those are are connected also to big experiments. Also, IFT acts as a host to other institutions, right? I don't have to tell you a lot about this one, right? But this other one is connected to the CMS group, right? So it's a experimental, high-energy experimental group that does a lot of also computing and outreach, as you can see from some of these slides, right? And finally, I decided also to highlight some of the IFT events, right? So we have outreach activities, advanced summer courses, right? And conferences, including this one. This is quite amazing. It's a conference organized by IFT students. It's now on the 46th edition, which is quite long, especially considering how young all the institutions are in Brazil. We also have now this effect of having the SAIFR here, that some of our existing activities are now merging with SAIFR. So this is a good example. It's a long-running winter course, winter in Brazil, right, that existed for more than 20 years, and more recently, about, I would say, 5, 6 years ago, we translated the name of the activity to English and made it a joint effort between IFT, SAIFR, and the Perimeter Institute, right? And it's being very successful transition, right? Also, we have been doing for the last 5 years, investing more time into outreach, right? Especially in presence in social networks and such. A fairly successful YouTube channel now with more than 20,000 hours watched in less than 5 years. Right? And so I invite you to check all that. And that's it for me. Thank you for the attention.
So let me start by thanking all of you for coming. So many of you came from a very long distance. And let me mention that we're actually celebrating 3 anniversaries today. We have the 60th anniversary of ICTP. We have the 12th anniversary of ICTP-SAIFR, which obviously is a funny number, but the 10th would have been the pandemic. So we're glad you could all come to the 12th. And there's another anniversary today, actually, which is David Gross. So David Gross is celebrating his birthday today. So David Gross is, of course, a model institution for us. I mean, KITP, he was the director for 15 years. And part of the reason for this symposium is to try to learn from him. And of course, we have other directors of centers here. We have Matthias Neubert from MITP, from Mainz. We have Klaff. We have many directors of here. So the idea is to learn from what has been done in other centers and try to obviously get the best advice for what we're going to do here. So that's your homework, is for the next 2 days, help us think about what kind of new things we want to do here. So what we've done up to now is, of course, mostly done by these people in the picture, which is the staff. So, of course, they're not here physically, but they are, of course, responsible for all of the reasons why we're successful. And the 6 people here are the faculty now, and hopefully will be growing soon. As Ricardo mentioned, we'll get some new positions soon. So obviously, another role of the symposium is to try to get people applying, because we need to have more good candidates. So the mission is, of course, what Professor Zago already said. We want to be the world-leading theoretical physics center, of course, in South America. And so one thing which hasn't been mentioned yet, was mentioned briefly by Ricardo, is for research training, but also for outreach, which I think is something that's very important in Brazil, to have interactions between universities and research centers and high school, because without the high school students, there's no future. So motivation, so I don't have to say too much why people are interested in theoretical physics. So of course, everything we do today is based on things that we learned in the last century in theoretical physics, and so hopefully, this coming century will be based on what's doing now. So we need to spread this knowledge, and of course, ITCP Trieste, KITP in Santa Barbara, and all over the world there are other centers that are doing this. But in South America, there are some small ones, but there's nothing of that scale. And of course, there are centers in South America which are very successful. So for example, IMPA, the Institute for Pure and Applied Mathematics, is a model for us. So of course, they're in mathematics, but they are very successful in bringing international people here and really doing first-class research. So the fact that it can be done is important for us. And of course, physics, because it has so many applications to all of science, it may have even more impact than IMPA has in mathematics. So why ICTP-SAIFR was chosen? So in Sao Paulo, of course, there are many reasons, but I think, first of all, it was chosen so we were the first partner institute chosen by ICTP. There are other partner institutes in other continents. So as already mentioned, IFT-UNESP is one of the oldest graduate physics departments in South America. And it's, of course, not only old, it's also very successful. FAPESP was already mentioned. It's probably the most well-funded agency in South America. And the other advantages, we're in Sao Paulo, which is, of course, the biggest city in South America, and we're very close to the biggest airport in South America. So although, you know, people, it takes 12 hours to come here, at least it's one flight. So most people can get here very quickly. So, and another thing which has been already mentioned is that we're part of one large university, UNESP, but there are other large universities, which, of course, USP, which is the biggest university, is just 30 minutes from here. And Unicamp, Campinas, is, okay, it's a little bit further, but it also has technological centers, which are very important for us. And now there's a new federal university, which is also close by. So we're, of course, we are small, but we're in the middle of a place where we can use, of course, the knowledge at the other universities. So we're very lucky in having these three advantages. And this is just some pictures. I'm not going to go through all of the history, but some things which haven't been mentioned yet is the Simons Foundation, which is a private foundation in the US, which has helped us. Perimeter is an institute in Canada. We have Pedro Vieira, and we have many joint projects with them. Another thing I want to mention is this opening ceremony. So this was 2012. So 4 people who had a very important role. So Carlos Brito Cruz, so he's now the president of our scientific council. Juan Maldacena is a very well-known physicist from Argentina, probably the most well-known physicist in South America. He's on our steering committee. Fernando Quevedo, who is the director of ICTP when this partner institutes were created. And Julio Cesar Durigan, who was the rector of UNESP at that time. So since that time, of course, there's another private foundation which has been formed in Brazil, which many people know about, Serpilheira Institute. The president of Serpilheira is now also part of our steering committee. And also, as was mentioned, there's this Instituto Principio, which is now, you'll see tomorrow, the building is, of course, the same building, but it's been reformed. So we'll see tomorrow what kind of facilities they have that we're also planning to have activities there. Finally, there's a private foundation, a private association, which was formed a few years ago, essentially to get a private funding. So it's been very useful for private sources like from Simons Foundation and from Serpilheira Institute. It's much more flexible than getting the funding through the universities. So of course, FAPESP goes to the universities and to the researchers, but our private funding all comes through this private institute. Okay, so these are some centers. So the 1 to 13 are centers that we have. Obviously, there are lots of international theoretical physics centers all over the world that we have connections with, agreements with. We have associated researchers. Many of you are associated researchers from all over South America, and these are current members of our steering committee and scientific council. So on Wednesday, we'll have our meeting of the council. Okay, just to see some things we've show that we've been successful. So we helped UNESP to be the #1 rising star in 2016. IFT has been the highest ranked, has gotten the highest rank from the national funding agency, CAPS, since ICTP-SAIFR was created. We got this award from the American Physical Society in 2021. So we're doing well, and as I mentioned, it's not just hard work on the sense of the researchers and staff, it's also that we're lucky to have these IFT-UNESP, Sao Paulo, and FAPESP helping us. Okay, so this is our financing. So we get, UNESP pays our staff, professor salaries, and of course the infrastructure here. FAPESP, so the infrastructure is of course through IFT-UNESP. FAPESP finances our schools, our workshops, our fellowships, so essentially our research activities, but not the salaries. ICTP, we have joint schools and workshops with them, and we also get funding through the National Funding Agency through our graduate students, and there's also some researcher fellowships. We also get private funding, which is different from, for example, most institutions in Brazil, from the Simons Foundation that I already mentioned, from the Serra-Pieri Institute, from Perimeter Institute. We have a professor who spends 6 months here and 6 months in Perimeter Institute. So that's an institute in Waterloo near Toronto, Canada. We also just have an agreement with a new private institute in UCLA, University of California, Los Angeles, involving another joint professor. So we're in the process of choosing now this joint professor. We'll spend some time here, some time in UCLA. And we've also been lucky enough to get some private donations. So private donations we're using to set up an endowment for research chairs. So one thing that we are suffering from, all researchers in Brazil are suffering from, is that the university salaries are fixed. And independent of what kind of research you do, essentially you get the same salary. And the salary is fine, but it's not competitive with salaries outside Brazil. And so we're trying to get research chairs like this Simons Foundation. We have research chairs for tenure track fellowships, which you can use to supplement salaries. So that's something hopefully that will be useful for attracting qualified people. These are the researchers that are involved on our grant. So researchers from all the different universities in the state of Sao Paulo. The ones in blue are the ones here that are working as the researchers of ICTP-SAIFR. We just hired a new researcher, Dario Rosa, which one of these J. Pesquisador fellowships. So he's actually working in quantum technologies, which is something that was already mentioned, is something that's going to be created, a new research project by FAPESP in that area. These are some numbers. These are the number of activities we've had, visiting scientists, students that have visited. We have all kinds of outreach activities. David Gross has already been here a few times. And just some pictures of activities. These are our schools. So we have schools in all different areas, 2-week schools for PhD and master's students. So learning topics which are obviously not taught in usual disciplines. And they're very successful. They're modeled after the schools in ICTP Trieste. Workshops, we have workshops in all fields. Of course, they're usually shorter. One idea, as we'll talk about in a little bit later, is to expand these short workshops into long-term programs for researchers where they can interact for longer periods and create collaborations like they do in Santa Barbara. So, of course, during the pandemic, everything went online, but we had lots of online activities, including a huge conference for strings, which was an annual strings conference. Outreach activities we have for the general public. These are going to be, I invited our 2 outreach coordinators to speak about them, so I'm not going to say too much about outreach. But one thing we did do is we translated material produced by Perimeter Institute for high school teachers. And so one problem in Brazil and all of South America is, of course, high schools are not well connected with the universities, and the curriculum for high school students is based on physics done 100 years ago. And the teachers are scared to introduce modern physics into the classroom because they just don't have the material that they can use to answer questions, to teach the students. And Perimeter has developed this whole library of material for high school students, for high school teachers to use in their classroom, which uses modern physics, black holes, quantum theory, but taught obviously using language for high school students. And we translated all this into Spanish and Portuguese, first into Portuguese, and then in Spanish, we got an award from the American Physical Society to translate it to Spanish. And so the idea is now to use this material to train high school students. So that's something we hope to expand. These are some outreach activities for high school students. So I'm going to stop here and pass to Rosario, who's sitting over there, to say something about some of the schools we've done together with ICTP.
Yeah, so I just yeah. Oh, he's coming. He's coming back, right? He's coming back, so hold your applause. So I spent 3 minutes about some joint activities that we have had so far, especially with ICTP in Trieste. So we already had 4 joint ICTP-SAIFR, ICTP Trieste schools on cosmology. And the first one was in 2014, and you can see the organizers, people from Trieste and people from here, and the lecturers. This was the first one. And then we have the second in 2017, the third in 2019. The idea is to have every 2 years a joint cosmology school. And the next one is going to be in 2021. Sorry, this was the last one was 2021, and we have another one next year in 2024. Actually, we skipped 1 year. Huh? 25, yes. So we skipped 1 year, and in that year we had a school in Argentina, the Giambiagi Winter School, which was also in connection with ICTP. So we also have we also had 3 joint ICTP-SAIFR, ICTP Trieste schools on particle physics. The first one was 2018, the second one 2020, and we have one this year, the third one in June, end of June, beginning of July this year. And we also had a joint activity which was very successful with Mainz Institute of Theoretical Physics. So Matthias Neubert, the director, is here, and he helped to organize this thing, and we are thinking of new possibilities for interactions with MITP. We already had some ideas of what's going on. So I think this is it for me now, and now it's Pedro.
Okay, thank you. So I'll just speak very briefly about 2 activities that we organize here at SAIFR. One is this Perimeter SAIFR Journeys in Theoretical Physics. So this is a school that we organize every year, where we try to attract the very top students from all over Latin America. We bring them here, typically around 100 students. We cover the flight for many of them, so it's quite an investment to bring all these students here for 1 week. We have 2 lecturers from Perimeter, 2 lecturers from IFT. And after this course, there are 2 days of 2 very tough exams on Saturday and Sunday, like 4-hour each exam. And based on the results of these 2 exams, plus the interactions we had during the students during that week, we select a few students, 2 to 4 students, to take part of the Perimeter Master Program joined with the Master Program here. So it's an opportunity where the students spend 6 months here, then they go 1 year to PI, and then they have the chance of coming back for 6 more months. So I think it's a very successful program. I'm consistently told by the people at PI that the students are amongst the top of the class every year. And it has been very successful so far, and the next one will take place this July. So yeah, so on the top picture you see some students, the closest ones that are talking to each other were selected in the last edition, and in the bottom it's Perimeter, and the student in the blackboard was from Colombia, and he was selected the year before. Another big activity we had, which was last year, was related to a big international collaboration that I'm part of, that is the Simons collaboration for the non-perturbative bootstrap, which is one branch of theoretical physics where we try to study strongly coupled theories by highly constraining them based on simple principles. And every year, this Simons collaboration holds a big annual meeting. This collaboration actually started through a set of informal conferences that we started at Perimeter a few years before. And then we formalized it in terms of this collaboration, international collaboration, and we got this big Simons grant, and the very first meeting was here in 2017, as seen in the bottom corner. And at that time, we hold this meeting here. So we had many hundreds of people. It was a huge meeting. And so we spread, people diffused throughout all the building with signs where people could take over offices all over. And this year, it was organized at Principia, where we will be tomorrow, very close to the hotel. We expanded from 2 to 3 weeks. The community grew a lot, so we had quite a big budget of $150,000, and it was a very big program through 3 weeks, where we had some informal talks in the morning, and plenty of time for discussions in a beautiful space, 3-story building with lots of space for discussions, and it was really an amazing event. And after it finished, people were thinking that maybe the last one could be also held here. But okay, we should probably rotate a little bit, so we'll do it in Madrid. And And it was very convenient. It was also very convenient to organize it through this foundation that Nathan mentioned. It simplified a lot the bureaucracy. The very first one, we had to channel money through Perimeter for each individual flight and so on. It was quite painful, and having this foundation is also very helpful if you want to organize some particular event with external funds that the funds can be managed locally. This was also very helpful. Okay, that's it. Thank you.
Hi, my name is Anna, and I am one of the outreach coordinator at ICTP-SAIFR, and I am very happy to be here today at SAIFR's anniversary, and also a little bit nervous. So be patient with me, please. And I will talk about our outreach activities, and as Nathan said before, our outreach activities are divided into 3 groups: for the general public, for high school teachers, and also for high school students. I will talk about the first 2 of them, and then Lucas, that worked with me, will talk about the last one. So for the general public, we have all kinds of programs, but all of them have the same goal, that is to bring together scientists and the general public. We do public lectures, as we did yesterday here, and those lectures we invite distinguished scientists to present their research to the general public, and those lectures, they happen here at IFT Auditorium, but also at Instituto Principia. And as you can see on these images, it's very nice to see that people are interested in what's happening in physics. So thank you for the scientists that attended our lectures as well. But we also have more informal programs. One of them happens in a movie theater, where we choose a movie and a scientist to talk about the sciences that is in the movie. And also a seminar that happens in a bar. And we think that having all these informal environments is more engaging for the public to ask questions and also to do comments, and also because they are super fun. So if you are free tomorrow, we are going to have a tomorrow evening, because during the day you have all the symposium. But we are going to have a session, a movie session with the movie Proof. And those sessions, they happen in a movie in Consolação, Cinema Belas Artes, so you are all invited. We also interview scientists to do videos in our social media and also for our website. We are now planning on working on a multimedia report for quantum technology that we are going to be published by the end of the year or maybe next year. We already done 2 of them, about particle physics, about astronomy, and also about complex systems. And many of you were interviewed for those programs. For high school teachers, as Nathan said before, we work with perimeter material that we translated into Portuguese and into Spanish. And now we do workshops for teachers learn how to use these materials in their classes. And these workshops, they happen both online and in person. And we have a special one that is a week-long summer course that is online, and it's for teachers from Brazil and different countries in Latin America, so they happen in Portuguese and in Spanish. And besides the perimeter activities, we also invite scientists to talk to the teachers, and also we try to virtual visit any scientific facility around the world. So this year we did a summer course in particle physics, so we virtually visit CERN, as you can see, and this image. And we also do in-person workshops, and last year we did our first workshop outside Brazil. We went to Uruguay, so you can see all teachers from Uruguay that attended our workshops, and it's really nice to see all these teachers that want to learn how to teach physics in a different way. So thank you, and now Lucas.
Okay, so hello everybody. My name is Lucas. As Anna said, I'm a high school physics teacher working in a technical public school here in São Paulo and also in a private school. As she said, I work here at ICTP-SAIFR since 2018, and I'm responsible for organizing activities for high school students. So today I'll be giving you an overview of some of these activities. So I will start out with our main and most traditional activity. Throughout the year, from March to November, we offer on Saturdays here in this auditorium many courses on topics that usually are not in the regular Brazilian high school curriculum. So here I mean relativity, quantum mechanics, cosmology, and much more. These many courses are, of course, conducted by physicists, and they take place since 2016. And by the way, Pedro was the founder of that activity here like 8 years ago. So usually we have from 50 up to 120 students and each Saturday. And it's really interesting because we gather very motivated students from different schools, from public schools, from private schools, from different neighborhoods with different social and ethnic racial backgrounds and gender diverse. So these main courses are inclusive and plural, which I think it's very important, especially in a country like Brazil, where the vast majority of the population has almost no contact with research centers. So an extension of these mini courses was launched in 2022. The winter course, which is a 5-day-long, more intensive and advanced activity. So we select 35 highly motivated high school students and they spend the whole day here from 9 a.m. to 6 p.m. So they attend to short-term courses from calculus to Python and quantum computing. They do exercises, they work on problems, and it's very interesting. Also, in the winter course, we have computational and practical activities. So the whole experience is really relevant, we think, for these students. So finally, we have had since 2021 the Summer School for Young Physicists, which is a program in partnership with the University of Porto in Portugal. And during 1 week, in addition to attending many courses, keynotes on different topics of physics, roundtable discussion about careers in physics, 40 top high school students have the opportunity to work in a group project under the supervision of a grad student. Well, we think that the whole experience of the summer school is remarkable for most of the students because working in a group project gives them the chance of understanding how the process of construction of science, although in a somewhat simulated way, really works. So now, just to finish, we also have activities where we go out and visit public schools. So we don't do just like activities here at IFT. So we have, as you can see, the physics games, which is a playful and fun activity for 12 and 13-year-old kids. Of course, it's an activity on physics and science, where basically speaking, they work in groups to answer some questions after a short talk given by a physicist. We also do the physicists at school, which consists of a talk given by a physicist at a public school, followed by an informal and free conversation. So it's a very, physicists at school, it's a very interesting activity because for most of these students from public high schools, it's the first time they will have contact with a scientist in person. So as for me, that's it. Thank you for your attention.
So far we've talked about past and present, and of course the reason why you're here is to try to plan the future. So the last few slides is just to tell you what we're thinking of doing, and we need, of course, your advice and your support for doing these things. So, of course, 2024 has already started, so we have the whole calendar activities for 2024. So these are the schools. So we have about, I guess, 10 or 15 schools and mini courses that will be taught on all different topics related to fundamental physics, to biological physics, to quantum computing. So as Atish mentioned, although we started essentially doing just high energy physics, fundamental physics, we're now trying to branch to all areas. So these are the schools, these are the workshops planned for this year. One workshop which Rosario is organizing is essentially for the high energy physics community, including cosmology, to try to strategically plan, the funding experiments for all of Latin America. So that's somewhat related to Silvina's question about how we can get the different funding agencies connected between the different countries in South America. But so 2024 is essentially complete, but 2025 is essentially, it's an open target. So, so as was already mentioned by Professor Zago, the idea is to try to expand our activities. And one expansion that we're thinking of doing, which obviously it's still in the thinking phase, is having programs. So these kinds of programs are, of course, KITP is the model in Santa Barbara. And one way of trying to coordinate the programs with the schools and workshops is divide the programs up into 3 different basic areas, in which the 3 different areas will be in different times of the year. So in that way, the schools and workshops, for example, related to physics of life, will be together with the programs we have on physics of life. So we get an interchange between the students and the researchers. And similarly, fundamental physics, which is high energy physics, cosmology, etc., we'll plan on organizing the schools and workshops in synchrony with the programs. And finally, the third set of programs will be on quantum systems and artificial intelligence, which was already mentioned. It's one of the new initiatives of FAPESP. And although at the moment we don't have so many people working in this area, the idea is to try to expand also into this area. Artificial intelligence, on the ground floor of this building, we have one of the directors of the new center, so Sergio Novaes, who is also going to be involved in these programs. So this is something, tomorrow you'll be going to Principia. The idea is maybe to have the schools stay here, the workshops maybe can be both here and at Principia, but the programs, which are the long-term programs, would be at the Principia. So near the hotel, near Avenida Paulista. It's a nice place for somebody to spend 2 months. Here, this is a beautiful building, but if you go a little bit away from this building, it's not such a great place to be here, for example, at night. So it's, so we're using these 2 facilities in order to maximize the attractive possibilities for researchers and, of course, students. So, so as I already mentioned, although our institute is very small, there are 3 large universities, there are actually 4 large universities nearby, and we invited people from all these different universities to come here because obviously if everybody thinks I'm only going to do things at my institute, then you're not going to be able to combine forces. And I think this Principia has the advantage it's not connected with any university, so it can be some kind of environment where everybody feels they're at home. So that's something that I hope will work very well, and tomorrow we'll see what these facilities are like. So this is your homework, is to think about how we can develop these programs in order to be useful, not just for our center, but for all of São Paulo, Brazil, Latin America, etc. Okay, so some of these activities are these long-term programs that I just mentioned, but there's something else which I think is missing in São Paulo, which most large cities have. So, for example, Paris, New York, Boston, they have meetings of different universities, but it's maybe a monthly meeting of everybody in a certain research area. So maybe you would have weekly meetings in your own university, but one idea is to have a place where people would come from the different universities. Obviously, it depends on how much time they have available, but once a month or once every 2 months, to just have a meeting where you might have 2 seminars. Maybe one of the seminars would be given by somebody from outside Brazil who you would invite, and of course we would help fund these activities. And the other people would be, people from local universities which would come together. So obviously they have to set aside a day which is convenient for them, but to have a meeting place where people can collaborate and instead of just working with researchers at their own university, be able to collaborate to the different universities. So a hub is really a hub, means it can't just be a center, it has to be a place where people come from other places. And I think these monthly group meetings might do that. So it's not something that's very expensive to do, but it has to be coordinated, and we could play the role of the coordinator together with, of course, the organizers in the different areas. So that's something that I hope you also talk about tomorrow, how to implement this. So those are the new ideas. One other thing that was already mentioned is the university promised us 4 permanent positions. We also have these tenure track fellowships from Simons Foundation, which, so Simons Foundation is a private foundation in the US, and they fund essentially research in, well, mostly physics and mathematics. So we have gotten now for almost 10 years this grant from the Simons Foundation, which we can use to supplement the fellowships. So the fellowship is fine. It's about 10,000 reais per month. which is good. It's a little bit more than a postdoc. But if you want to attract a tenure-track professor, you have to pay a little bit more than, you have to pay more than just a postdoc salary. So this essentially doubles the salary. So, so the idea is, obviously, we have to attract top people to these positions. Otherwise, well, we'll stop getting funding from Simons. There's not much point if we're just getting postdocs for these fellowships. So we have to attract top people. We have a search now. One search is in the area of physics to biology. So members of the search committee, Bill Bialek and José Nelson Onushik, are here. And we also have another search in all other areas. So Eduardo Fratkin is here. David Gross is, of course, here. So although we've advertised this, applications are still open until the end of February, and we're asking for your help in spreading the word, because although I was actually surprised, we have not gotten as many applications as we got in the past. Part of this might be because of the pandemic, that people are not so eager to travel to foreign places. Part of it is, of course, the impact of the previous government in Brazil, which Brazil is not as attractive as it was before. But I think now Brazil is starting to get the attention of scientists. So hopefully we'll be able to get very good people for these positions, and of course for the 4 permanent positions that were promised by IFT. So as I mentioned, of course, we have these research chairs, which can also help with us. Okay, so again, I want to hope that you all enjoy the rest of the symposium. We have also these social media places. And finally, I want to pass to Vahana Gabriela, who can say some final words. So thank you very much.
Good morning, ladies and gentlemen. I'm very glad to be here in this event, and I'm very happy with the initiative of ICTP in South America, and to establish this initiative in the city of São Paulo, in IFT-UNESP, it's very glad. We from the state of São Paulo, we are very lucky that since the end of 19th century, our leaders have had understood that only with science, technology, and higher education we can develop this state. We were a very poor state in the end of the 19th century, and now we are the strongest state. Nowadays, the government invests almost more than 7% of the budget for higher education and for the research institutions, and for, of course, for FAPESP to support the research. And now we are very much concerned about the internationalization. It's not possible for this globalized world to have research, isolated research. Of course, in the 20th century, we have a lot of initiatives, mainly just before the Second War, when we attract 40 very good scholars to establish University of São Paulo. But we started mainly during the last decade with the mobility of students and mobility of the faculty members. Later, we decided to make these links among the institutions in the state of São Paulo and the foreign institutions stronger. So to make it stronger, we encourage to have joint research projects. Nowadays, of course, in order to create an international environment for education and research, we are encouraging to attract, we are trying to attract foreign institutions like ICTP to come here, to establish here, to have this international flavor inside the state of São Paulo. Of course, our intention is not to attract only the international institute. We include the research labs from the companies also to come to São Paulo. And hopefully we are managing to attract some companies here. So thank you very much for this opportunity. Thank you very much for coming here to São Paulo, coming and establishing a very important nucleus in the state. And I'm sure that we are talking the same we are changing the same ideas, we are talking the same ideas. Thank you very much.
Okay, so now we have a coffee break, and we'll be back, I guess, I don't remember what time, 10:45? Thank you.
I suppose. Yeah.
Okay. Thank you.
Like this.
Thank you.
Say who you are and all that. Announce yourself.
Okay, so I'm Silvio Canuto. Well, first of all, I should say that I have good memories of many years back when I was talking to Roberto Krankel and Gaston Krein, and they were commenting to me that the Institute of Theoretical Physics was considered to have a branch of the ICTP here. So I'm very pleased to see the success it was. So, and also to see how fast time passes. So it's very pleased to be here, and congratulations to all of you. So I have to answer, how can the physics community increase its contribution to society in South America? Now in 2.5 minutes.
Well, you give you 3.
Okay. So I have to be very objective, so I have some written words here. So I think this is an interesting, important question. Of course, there are, of course, many ways that we can contribute. So the point now is to pick one and argue in its favor. So the point I decided to pick was rescue. I call it the rescue of neglected young talents. So university must interact with society. We are all very aware of this now, but not only because it's supported by public funds, but also because the society is the strongest ally to defend the university and the science when it is attacked by many reasons, including negationism. So there is a decrease in the number of students looking for education in science. So that suggests that we have to honestly rethink our courses and our aims. But I will skip this because I want to go directly to my point. And the point I want to make is that I think we are failing in not being in touch with society needs, which includes providing more than professional in line with society needs, for instance. So we have noticed in recent years that there is some students abandoning, especially courses of physics and mathematics. So why our students are abandoning the courses? So I think we must make it more attractive. So hence, and this is my central point for this discussion, we must reach young students even in high and secondary school levels, showing the beauty of science and its importance to development in general. This is somehow along the lines of what Pedro Vieira just mentioned, presented half an hour ago. So I think we could attract some brilliant minds in the lowest level of our society that are socially neglected and give them the opportunity to develop their own vocations. Many, if not most of them, do not even know that the university, and I'm talking about USP, UNESP, and Unicamp in particular, are for free, and there is even partial financial support to maintain these studies. So the university is becoming less attractive, and the society price can be very large. So I guess I'm touching two complementary points. One is the university and science courses must reconsider the changing society and the new demands. And the second, there are talented youngs, boys and girls, that could give important contribution to science, and they are wasted, and we must reach them. We have to visit schools, bring simple science experiments, show the present challenge of science, and we have to extend our arms, showing the beauty of science and the opportunity they certainly can have. My last sentence here. There is a future, and we must show it to them and to us. Thank you. This is my very modest contribution. Thank you very much. Thank you.
So my name is Carlos Greff, and I had the pleasure also to see how ICTP-SAIFR grown so quickly. I was vice president for research before Edson, and I had the opportunity to be here in one of these meetings, and it's quite amazing. And congratulations, Nathan, and all the people who are involved in this initiative. So I would like to stress 2 points, I think, that are quite valuable for how our community can impact Latin America. And these 2 points are education and outreach, which was basically the things that are being done here are marvelous. I can't put words how good the job is being done here in all of its senses. But also we have to think about research and innovation. On the first place, on education and outreach, I think this is valuable for any society, but especially here in South America, that any society that can give fair opportunities for its people will do well. That's the most valuable thing in a nation. A nation is not a piece of land. A nation is the people that are inside it, and every country that does well in being fair, bringing, as Silvio just mentioned, everybody that has talent to outperform, to do what he can to make society better. That's the goal of any society. And the better, the more open, especially in these days. So if we go to South America in general, we have some advantages that we are far away from everything, which is good and bad. So in a sense, it's time for us to maybe work more together and really try to develop. So I'll stop here on the outreach and education, and I'll go very quickly to research and innovation. Of course, the other point that is very important for the impact of our activities is research and innovation. And we have many nice examples here, and I'll just talk about briefly of 2 areas where physics is very important. One is on the energy transition, which is really coming to us. If we like it or not, it's coming to us. And Brazil, of course, is one of the places where this is being done for many years. We have this bioenergy program. We go out and we see ethanol, and we can drive our cars on a renewable energy source. But nowadays, there is other things like hydrogen and green hydrogen that are popping up. And I would just give one example of a research group in Campinas, which worked close to where I did my PhD, and who has generated a startup which is called Hydron, which is probably the most important way of transforming methanol into hydrogen. So our ethanol, which is sugarcane based, can now be probably a source for hydrogen, which is hydrogen carrier. That's quite important. The other area where physics is very important in society is on medical physics. So I'll just stop there. So in medical physics and in Ribeirão Preto, where I was a professor there was a guy, Guilherme, one of the first in medical physics, and he's just started a startup which is making implants, and it's getting all over the world. He got finance from Germany. And so we have changed, I think, in these 2 areas. So thank you very much for the opportunity to talk a little bit.
Oh, okay, thank you. My name is Marcelo Knobel. I'm a physics professor at the University of Campinas, Unicamp, here nearby. I'm glad to talk about after Graf. He seems older than me, but we were classmates. We studied together physics at Unicamp, so it's a pleasure to be here discussing this issue which is really, really important. Of course, I would have many things to talk about, but I would like to stress what I believe is really, really important in our field, especially. We are all scientists, work in different areas of science, here mostly physics. And we don't have this approach when we try to discuss and talk about science communications and science popularization as a whole. Everyone guesses what is the best and try to do something and try to, of course, everyone has the best of the intentions, but it's not always the best. There is a field of study which is the so-called the public perception of science. There are surveys. There are many, many data which are used in order to understand the response of the public to science to higher education, and we are not using that as much as we should do in order to give a scientific approach to these science communications. We are failing in our communications, in our institutions, in our universities. We are failing. Take a look on how many followers you have, well, UNESP has in YouTube or in Instagram or whatever, or Unicamp or USP. It's not enough to reach as many people as some so-called digital influencers are reaching. What are we doing which is really wrong? We know that science is nice. We know that science is really, really important for society, but we are not able to communicate it properly. We are not finding the right communication with the young population. So I believe that we should try to follow this scientific approach to science communication and, of course, make it better, make it more suitable for the society as a whole. I could talk on many aspects of science, and of course, there is probably one thing that Deborah will talk about is about reaching more women to science, to physics in particular, how we can attract more minorities and so on. So there are many challenges that we have to face in order to make it happen. I just saw a few days ago a recent survey in America, in the United States, claiming that the trust in institutions is the lowest possible, and in particular, the lowest possible in higher education. Most of the Americans nowadays, they don't believe in higher education, as well as they don't believe in science. So we have to tackle that problem really seriously. Thank you very much.
Well, I'm Débora Menezes from the Federal University of Santa Catarina, and today I think I'm wearing the hat of CNPq, and I will change a little bit gears, and to try to answer this question, I'm going to show you some data, and then you can make your own conclusions, but the idea is to say that if we increase collaboration, scientific collaboration, we also help the society. Of course, looking around, I see 5 women, out of 40 and something people, and I've been paying attention at all pictures that were shown during this morning session, and we do not see women at all. So we do have to work towards increasing diversity. This is women are 51% percentage of the society, so we cannot just disregard these numbers. But this is something that I've been doing at CNPq. So this is one panel, and it shows from 2005 up to today the amount of money that has been spent towards international collaboration. And then this is in physics. So you see this bump in the middle, that's Science Without Borders, and then you see that it's increasing over the last 2 years because of this FNDCT. So we have to think about how to use this money properly. This is another panel, so if we look at the amount of people with doctorate degrees, then we can also look at sex and gender and age and everything, so you can follow these numbers afterwards. But the idea is that we have we have to do lots of work to improve these numbers in physics. All those numbers were taken from CVs that were updated in the last 5 years. And then you see that we have around 9,000 people with doctorates in physics. Most of them are working in academia or scientific institutions. And so they can really help to improve this picture. That's people that we've been forming in Brazil and are now working somewhere else. So in physics, just 49 people have been formed in Brazil. That you see, all of those people must update their CVs. So I see that maybe this is there is a little bit more than that, but there is no doubt that there is room for improving these numbers. If we look the amount of people being paid. This is people that are currently being paid around the world. This is not physics, this is everybody. You see lots of people in the United States and some people in Europe and so on and so forth, but you see 6 people in Argentina only. And then if we move to physics, you see nobody. So what's happening with our collaborations, the question was about South America. What's going on? So this is something that we need to have in mind. We also have to improve these collaborations. That's it, thank you. Wow, I'm very good at timing.
Okay, my name is Silvina Ponce-Dosom. I am a physicist from Argentina, and now I am president designate of the International Union of Pure and Applied Physics. And so there are many aspects that we can cover with this title of Physics and Society. Some of these aspects have been covered sort of before, like for example, trying to get from our physics community, trying to get involved into improving science education at high school level, the initiatives of generating new materials so that can be used and training high school teachers is a very interesting one. And something else that I think is very important, as Deborah mentioned, try to strengthen our relations in the region in various aspects. On one hand, scientific collaborations, but also in other aspects that have to do with the way that we relate to our societies and also how we organize our own institutions regarding diversity, for example, that we can share through workshops and activities, initiatives to increase diversity. But now regarding how to relate to society, I think it's very important to try to promote projects of co-creation of knowledge with the society at large. There are several experiences in various parts of the world, in particular in South America, and we can try to, I don't know, promote the funding of those types of initiatives, because in that way you relate directly to people that are not members of the scientific community, and you can change the perception towards science. How to combat anti-science or the use of social networks to propagate fake news or incorrect information, that I am a little skeptical. I don't know how to do it exactly. I don't think you can do it through a rational sort of speech. I am very pessimistic in that regard. I am a little hopeless at what to do. Of course, we should try to use social media to change the perception, but to me it's not completely clear how to do it. In our region, there is a great digital divide, and I think that we can contribute to try to at least give some tools to people that don't know how to handle digital tools. Particularly, there is an inequality there in gender, with women less able to use many of the tools that are available in cell phones and stuff like that, and maybe we can think of contributing to that. And then there is the issue of sustainability. The UN has declared the Decade of Sciences for Sustainability starting this year, and I think we should use that opportunity to strengthen our collaborations and think how the physics community can contribute to sustainable development in the region. Well, that's it.
Hi, I'm Ado Jorio from Belo Horizonte, from the UFMG. Okay, so first, yesterday I have 2 daughters and they are in the age of choosing their careers. And then I was very interested. I was like reading on different universities, what is major, what is the job they have, what is this for? And then they say, oh, the psychologist does this and that. And then I was curious and said, what is the physics? And then there was this university, it was written like this. They are smart people, they can help somehow, you know. So if you think of the time we are today, and you try to spot where the physicists are helping, let's give a step back. If you look all the industrial revolutions, we were always like responsible for everything that happened, okay? Like the same thing was for the semiconductor physics, and this shaped the world that we live today. And the expectation for the next cycle of economic revolution, etc., is related to artificial intelligence and these things that are not a computer science problem. It's a physics problem. I heard today about the Quantum Initiative of São Paulo. We know about nanotechnology, we know about photonics, about optics. So there is no question that our place is always on shaping how the world will divide and will restructure its industry. So this is my view. And what we need to do urgently is to have more experimental physics. We need to, in Brazil, in Latin America, we need to make more effort on our teaching, on our laboratories to enhance our experimental physics, because this is our connection to society, to technology. So this is my contribution.
Okay, we should open it. I don't know if this was expected, but people have questions.
You can stay there. Thank you. It's kind of a question or a comment. Everyone touched into the science outreach thing, and of course, everyone will agree. The question about the pseudoscience, what's the difference between Earth, flat Earth, and round Earth? If you make a nice movie and you show on YouTube, it's the same. The thing about science is experiment. The thing about science is showing that we can ask nature to tell us how it works, right? So I think one problem with a lot of efforts of science popularization is that they do nice graphical things. They do nice things over the internet. But these things are exactly the same thing as any pseudoscience. We have to do things in the lab. We have to go lab to the schools, to primary schools. So Deborah mentioned about the gender. We see here, of course, the gender imbalance. We see, of course, color imbalance. Of course, we are not a fair sample of the society. How we can change that? There are things we don't see, like income. I'm sure we are not a fair sample of income of the society. So this also is to the basic schools, primary schools. I think ICTP-SAIFR has these super great programs of science popularization. Some involve experiments too. But usually all efforts go to some elite, even like a public elite school. I think the only way is to reach really like a normal school where normal people live and we do experiments. I think that's like the main concern, doing experiments to show what science is. Thank you.
Yeah. Can you hear me? Yeah. I think it's not the same. We do not do the same thing as these people that work with pseudosciences. They have three different appeals we do not use. They appeal to emotions. We do not do that. When we say something, it's plain and simple, and we think that's good enough. And they have money behind, lots of money. And the only way to avoid that is not increasing. Of course, we do have to increase the amount of outreach and videos and so on and so forth. But I agree with Sylvia. We need laws to avoid this boosting of fake things to spread. And there is lots of money behind that. So there is a project that has to be tackled at some point from our federal government. And then there is a third thing that's also related to emotions. You see, they know how to two different things that they normally use. One is if you're afraid of something, you just pay attention. And then you just send these things to people that you like through WhatsApp. Then it's out of the control of this social media that can be controlled. So it's really very difficult. It's not something simple to fight pseudoscience. And I have personally, I run a YouTube channel and a TikTok channel that's called Women in Science. And the TikTok channel, for instance, there are some videos with 400,000 views. It's a lot. But if you look at the profile of the people that watch, this is really science, it's same kind of people. You see, with my project, I do not reach people who have no studies. I do not reach religious people. And this is another point. You see, some of this information, because it's not just, this is disinformation because it's this kind of thing that is, the aim is really to gain money and to attract attention for something that's not correct. So without the law.
I would just like to complement in the sense that we always lived in a kind of a virtual world. So always was narrative, was what pushed people to some direction, either religious or culture or anything. We always lived in the virtual. It's just that now we are bringing this virtual world to some more concrete manner. So we have these screens and so on, and videos that you can make. So it's hard to compete in this sense that you are making. How can we compete with pseudoscience? Because we're competing with some kind of narrative that, as she pointed out, is probably even better for the common people that have little access to knowledge. Because they think, and if you think about neuroscience, most of our memories are based on emotions. So if you play with emotions, you are doing the right job to really get people's attention, as she mentioned, like fear and other kind of emotions that you can create. So I don't see that this may be a fair competition between us and these people, because they are using the instruments that have been used for thousands or millenniums of years, that is really to try to convince people of ideas, of this virtual world that they are creating. But what we must do, as I told you, to be a fair society, is to give people the opportunity to choose. So if you give people good education, they are already in a better situation to decide than someone that is purely ignorant. The purely ignorant will go all for the emotions. They will have no chance to choose between a video that is very well done with 1,000 likes or 1 million likes, and another which is 100. They will just follow, no, this is the truth. They have no idea what is the truth. So this is the thing that we must give this. That's why I think education and outreach is fundamental for us to get out of this bubble. But it's not a simple job. I mean, we are not talking about people that are, let's say, playing fair, if you want to think like that. They are playing big games. But that's what I would like to mention.
I want to emphasize again what I said about co-creation of knowledge. I understand that we cannot, all of us, turn into people that are going to develop that type of projects, but that also serves to communicate with the communities that are not part of the scientific community, and so that they gain confidence and they take part in the development, in the collection of data and stuff like that. There are, for example, one of the initiatives that I know that is run by a person who works on climate science in Buenos Aires. It's together with an anthropologist and people who grow crops in the Chaco of Argentina. And they collect information on rain, and they developed an app for cell phones, and students, high school students from those communities enter the data. And so I understand that this might be a drop in the middle of a huge ocean, but it's not just us being the owners of all knowledge that are above everybody telling what's true and what's not true. I think that you need to develop some confidence and this contact through the listening to what they need and making them part of the whole scientific endeavor, even if it's not very high-level scientific endeavor, but I think it changes the perception of science too.
Sorry, I had a comment in a slightly different direction because I thought that someone was going to bring this up, and so I'll throw it out there. So we've heard of many of the things that are obvious we need to do, and we need to do more of the same or increase how much we're doing it. But something where we are sorely lacking in South America is in the engagement with decision makers. Our politicians care very little about science, and of course, we could take any random speech of a president or whatever during the pandemic, where it would put a plot that wouldn't distinguish a linear log plot, they wouldn't know what it is. So already we're making, we are weak in the way we engage with the government. So if we see what is going on in the first, developed worlds, they typically have a strong science society or strong physical society that's lobby continuously to the government. We typically don't do that in South America. At the same time, we are also very bad because we tend to think of universities as these ivory towers that are highly detached to society. We also have to understand and do a mea culpa, that we're part of the problems. We're not engaging in the right way with both decision makers and power makers, so those that have the funding. We heard this morning that it's difficult and how much effort has to be put in to establish even a foundation where we can get some more flexibility to adapt and more readily to potential opportunities. So we also, I think we need to look inwards and then how to become, and ask ourselves how to become more relevant. And with that, have more power to actually change things. So I'd be happy to hear any of your comments on this.
I think one important aspect here is our science really useful for economy and society? Are we producing, generating money for our countries? Are we generating innovation? Are we doing the things that call the attention of the policymakers? I'm not sure we are not well represented in decision makers. Somehow we are. But I think we have to improve our connection to industry. We have to improve our capability to do innovation. We have to change, like someone I was discussing earlier here, they were saying if you put $1 million in the United States to buy equipments, 90% of the money run the economy. We send 9% of the money abroad to buy equipment. So we have to change this picture. And this is one aspect. Of course, there are other parts, but this is one strong aspect that we have to work.
Yeah, can I? Yeah, I agree with Adu, but I also agree with you. SBPC has one person, one lobbyist, and CNPq now has one as well. So, 2 people. But one thing I noticed is that when this guy goes to these people at the parliament, they have special money that they could give to calls for CNPq. And they really want to give money for scholarships because they understand what it means. But when we say we want money for science, for, you know, to pay project, then they don't want to give the money. So we do have to make an effort for them to understand the importance of doing science in Brazil. I don't think they do. And maybe 2 lobbyists are not going to be enough. So perhaps those scientific societies and institutions, they could foster this, I don't know, pay for lobbyists. I really don't know how to do it, but I also think it's important.
Just very quickly, we saw in this morning the creation of IFT and of USP, UNESP, Unicamp, and of FAPESP. And this was done by the policymakers. So sometimes, if we really reach these guys, things work. How we do it, it's not so simple. It's always like everything in life. There are some people that are talented, and they see the opportunity, and they do it. So we see here the example of how this can work and how it changes the society when it works. But the way that that's done is something that it may be not so simple, but we should look at these examples from the past. And if I go outside of Brazil, in Argentina and so on, you have a Nobel Prize that we don't have. So what was so different before that is not working anymore? That's something that we should ask ourselves.
Well, let me just give the pessimistic side of what Graf just mentioned. On the other hand, we have the opposite. I agree with the colleague that once everything is built, it's very easy to destroy. And this is the main problem. You saw in Deborah's graph, it's not by chance that we had a minimum of money in the last 5 years or 4 years ago. It's clear that there are a new political wave in the world, which is anti-science, denialist of science, and they believe that they don't really believe that science can make a difference, and therefore we are in danger. But we as a physicist, as a scientist, we do live in general in an ivory tower. We say, I don't want to care about that. I have a project to write or something to care about, a paper or so on. We don't care. And this is my main point. We all should engage in order to make a clear point that science and education is absolutely fundamental for the sake of humanity.
I don't know where the person who started this thread, where are you from? Yeah. Okay, and now where? In Canada. I disagree with you because many countries in South America, well, at least Chile, Argentina, Brazil, we have ministries of science. Argentina used to have until the new government. And the people that are in front of those ministries are scientists. Or where?
Not in Brazil.
No? It was Rezende? Was it?
He was the only one.
And what about now? She's not a scientist?
No, she's a politician. She's a very good one.
Okay. Anyway, but the thing is, I think that the main problem is continuity. For example, in Argentina, there was a law to fund science that was approved by Congress, and it was meant to increase the money invested. But there is no continuity for whatever reason. And maybe one way to guarantee that those policies that sometimes they are started and approved by Congress, that they keep on existing, is through international support. If we had some sort of regional funding agency or something like that with agreements that would be more difficult to cut because of political changes, I guess that would be a way to stabilize. Because I think that the main problem is that we don't have continuity of those policies, even though they are put into a law, like it happened in Argentina.
So I have been silent, but I want to make comments since the first question. So I'll be very brief. First, I think the key word here is science education. So if you have science education, I don't think there is a space for, for the pseudoscience, or at least there is less space for this. There's no one who will question that if I drop this pencil here, it will fall down directly to the floor. So, and that's one aspect that we also need is because elementary school or high school students, they must have education also in the sense that when they go to the university, they know the importance of experimental physics. So when I was a student, in my school, there are several experiments in physics and chemistry and so on. Today, you don't have that anymore. Now, if you look at the development of science in Brazil, you'll see that before the Second World War, there are very good experimental physicists in Brazil. And there are very good experimental people also, of course. But then, at a certain moment, particularly in 1968, when it was decided this new university program, so CAPES was making effort to increase the number of doctoral degrees and so on. So at that moment, two things happened. First, I have to say that I think it was very successful, politics. As we say, that was the closest we would get to something that's not political, but was state policy. Now, if you look at two things happening. First was that there was a need, or there is a motivation for increasing the number of postgraduate programs. And the reason for doing that, the easier way to get that was to increase the theoretical physicists. So most of the programs that were open, they have an emphasis in theory. That's number one. Number two, as the emphasis was in increasing the number of doctors in the country, what we have seen was that the number of programs increased without direct connection to the society. And that at that moment also, there was an emphasis in the education at university, not necessarily in the lowest education, elementary school, what we call ensino médio, which is not médio, by the way. It's anyway. So I think that was a very successful policy, but paid the price that the university was detached from society in the sense that they are not looking at the problems of society, but instead we are looking at the problems that could increase the capability and the merits that CAPES would recognize, and meaning number of publications, number of doctoral degrees, number of programs in the university, and so on. This is a moment that we can rethink this, because we are moving away from the society. We will not survive, the university will not survive seriously if they not look at the problems of society. So the point I want to make in my first how should I say, call or whatever, is that we have to dedicate more effort in the elementary or mid or high school and so on. Basically, I think it's time for us to look at the problems of the society, and especially science education.
One last one.
Okay. Oh.
No,
yeah. Sorry. Is it me? Okay. Well, when you read the question posed to the panel about the future, about the contribution of physics to society, it occurs to me that the future of society, unfortunately, or maybe fortunately, is not us. The future of society is made by people who are much younger than us, by children. When we as university teachers, university professors, we talk to students, they are undergraduate students, they are already grown-ups, they are adults, they have fixed opinions, they are more or less fixed in their personality structure, they know what they think, and I guess as we all know from our experience in the classroom, it's very hard to change their opinions. If we want that the future of society takes into account the values science, values diversity, values inclusion, understands the difference between science and pseudoscience, we have to learn how to talk about these things to students much younger than those we usually talk to. We have to learn as a community of university professors and professional researchers to talk to high school students, to talk to students at the age of 15, 10 years, maybe even younger than 10 years. And that's an enormous challenge. And that's not the typical target audience, say, of universities, but also not of the institutes. So I would like to pose the question to the panelists from your point of view. How shall we go about changing the future of society by talking to today's children?
This may not be, a big effort, but many of us are sometimes called to speak in a school, like for children, for, as you said, 15, 12, 10 years old. And, unless we are very bad teachers, usually they are very excited. Usually they are passionate by what you show. Of course, you downgrade the level. But these are efforts from, that we do, yes, on the individual level, and after that, that you have to do the project and the teaching, blah, blah, etc. So this probably goes along the same line that Sylvia was saying, that we have to pay attention to the basic schools.
Okay, so we'll try to be on purpose a little bit polemic here, but there's at least two approaches that were mentioned here to try to fight the wave reflected in that plot, right? One is to get closer to society, right? And here I must say, the whole idea that politicians are really deciding stuff is not true for most politicians. Right? Some politicians are really leaders. Most are just resonance boxes, right? They are just reflecting the voters, right? And the problem there is with the voters, not the politicians mostly, right? We're losing society for a while now. And so one approach would be, we heard a few examples here, try to get down from the ivory tower and go near people and participate in their lives in a way that their connection to us is emotional, because we'll get to them by this emotional attachment, and then they will be able to hear our rational arguments afterwards, after they like us, right? Not before. But there's another approach, which is try to stop that wave, right? Like to silence, like Deborah mentioned already, try to make laws that forbid the spread of misinformation. In principle, one could think, well, we have to do both, right? They are not antagonic. But I'm not, and here's the polemic statement, I'm not sure they are not antagonic, right? Most of this movement uses, every time science people or any kind of authority tries to silence this, they use this as an evidence that our arguments are not that good, and that's why we need laws to stop them. We cannot answer on a level ground, right? So my question is this, right? Trying to force to stop the spread of misinformation sometimes will not reinforce this idea that we are sitting in ivory towers and trying to tell everyone what to do.
Yeah, a brief question to the panelists. I mean, I think we all agree that bringing the science, putting it in perspective on the benefit to society is very important. And also in doing outreach so that we can attract people to be excited about science overall. In the US, there is increasing value being put for scientists and also for funding agencies, meaning giving support to those activities. Okay, both, you know, presenting your science as how it can benefit society and making outreach activities. How do you see it is the situation? And it's not ideal. It's just, you know, it has started in the last several years. How do you see those things being considered in Brazil or in South America? So how? In the past, I think in the US, it was kind of penalized when young people were putting time off to do outreach, as an example. So how do you see it is the situation from your perspective?
So let me tell you about my own experience in Argentina. There was like a governmental decision at the level of the National Research Council, CONICET, to value those contributions, to say, well, if you do outreach, that's important. You can even have money for outreach and stuff like that. Then when you go to the evaluation committees, which is us, because it's formed by our community, the culture of the community is very old-fashioned. So it's super difficult to get the members of our own community to accept that those contributions are as valuable as publishing in a top-ranked journal or have a good age or whatever. So it's very hard. I mean, it's our own culture. So if we want to change the way that those things are valued, I think we have to also train our own community into giving more value to those things. That's my own experience.
Just very briefly, so we are cooperative people. So I think things that are doing here, ICTP-SAIFR, it's popped up from below, and it's doing a great job, because we cannot, as individual person, try to do everything, but that's not how society works. There are specialized people that can do better. So things like what Nathan is doing here, I think it's the way. It's not that the university or the funding must come, of course. But probably we have to find alternative ways to do funding, because that's what she is telling us. People from the academia will always have a culture and saying that, oh, what is more important is to do research, is to do good education and so on. And it's hard to change cultures. But if you find some alternative way, like they did it here, like Serra Pilheira is doing as a new funding agency, some alternative ways to put people to do this job that not necessarily are on the same path as a researcher in the higher education. I think this is probably some way to get out.
I was wondering, when we think about the interface between the scientific community and high school students, elementary school students, so on, there's an obvious bridge, which is the education of teachers. Many of us are university professors. High school teachers go to universities. In the US, there's a huge divide between the elite research universities and the ones that actually educate teachers. And so you could point to that and say, okay, that's a place where we screwed up, right? So we can't sit around and say we wish they had better education when we don't actually engage in teaching them. What is the situation in Brazil? Do high school teachers of physics go to the universities that have great research programs, or do they somehow go to other institutions?
I think the situation is very bad. First of all, because there is a huge prejudice against physics teachers at school. The second point is that young students are not educated by physics teachers. They are educated by people who learn education and know absolutely nothing about science, nothing. I remember when I was a student, I used to plant beams. It's the same. You see, they don't look at the rainbow, they don't look at lands, nothing, they don't know anything. So there should be a point where we would be able to teach a little bit of science to these people who were teaching young students. Because I agree with Marcelo, he said something here that when faith is installed, we cannot fight it. It's very difficult. So we have to open the minds of our children while they are still children. And they have contact with teachers who know absolutely nothing about science.
Can I make a comment?
But
Can I make a comment?
yeah, but the question was probably about high school, not elementary school teacher. High school teacher.
I will go back to the beginning. I mean, without educating our kids, no? I mean, with diversity, it's impossible to break up the problem with the ignorance. So it's very hard, no? You know, probably we all have colleagues that even the vaccine during COVID didn't want it to take. So it's very hard. We need to start from the beginning. And I saw a program, I witnessed a program that we have to think. This is above physics, science in general. To collect diversity. How we do that? To try maybe to think about getting students from public schools, poor students that probably will have no opportunity before the high school, and then have programs to select, will be a little bit of students, of course, in the beginning, maybe 100, and educate at the level of the high school with the state financing it. Then this, of course, will give a little money for these poor people, that implication is diversity, and allow them to go to the public universities. And then, of course, the families will start to appreciate that,
and so on. So we need a multiplicative effect and get talents from diversity. And this is valid, at least as far as I understand, in South America, probably in Central America with the poor communities. So we have to start to think on that. But this is, of course, is beyond physics, is our science. So this is, I witnessed that. There is a program in the state of Piauí that did that. So it's not, I just saw that. I was very surprised, and maybe we have to think this much more wider.
Okay, just a comment connecting the previous and the, we have to look at numbers. Here in Brazil, only 20% of the age cohort from 18 to 24 years old are going to any higher education institutions, and from that, only 23% going to a good university, a public university, and so on. So we are talking about a huge minority of people who to study for becoming a teacher, and nowadays in Brazil, for those who are not from here, today we have more online education in universities than face-to-face education. So we are facing a really, really problematic moment in Brazilian higher education. And, but one point is also important to mention. I would make the polemic talk that Ricardo was trying to avoid, but it's not necessarily true that higher education would lead to be, you know, to be real sage and rational. So we saw thousands of doctors here, medical doctors, claiming stupid things during the pandemic, and they were to universities, as far as I know. So this is something that it's not, there is no direct correlation between education and you know, to be in the nihilism or to be really really smart regarding the response that science can make. So this is a very, very complex problem, and again, I would say that we should try to understand it more instead of just trying to guess.
So very briefly, I agree with you, Tobias. I think the key word is science education. You do not going to change society if you don't educate, you know, the youngs. So the question was posed here was, in fact, how the physics community increased its contribution. And then Klaus brought it to another level. But it's still, Klaus, I think the key word and the answer is still education. So when you say that the politicians do not represent us, we have to be very careful because they are elected by us. So yes, they represent us. What we need is a better society understanding to understand the importance of things in society so that they can elect better representatives. And the other aspect is related to what you said. We have an enormous deficit of high school teachers. Enormous. We're talking about 80,000, 100,000. It's enormous. What are we doing? What are we doing to solve this? I would say very close to zero. So we have to rethink many, many problems, many, many problems. And I don't want to elaborate more than this because that will bring me so far away. So I think I have to close, but I'm available if anyone to discuss or teach me about this. Thank you.
I have restrained myself until now. So I'm going to comment. All of this is great and good, but this is fundamentally a political problem, in my opinion. Okay, so there were waves during the history of the world where dark forces actually took over in Europe in the 1930s, and we are seeing a resurgence of that. Okay, until a few years ago, very few people refused to take a vaccine. Okay, this is a political problem, centrally, and it is upon us to have some degree of activism, because it is actually going to be one of the political level, at the society level. It cannot be just education is great, that's the long-term solution, that's what we always need. When I tell my dentist that I am a physicist, he makes a face, but this is scary. And I say, well, what people think when you tell them you're a dentist? Okay, but you know, that's a standard thing. People think that what we do is difficult and, you know, esoteric and all of that. But what we are seeing now is a political problem, essentially. And it has to be solved in that arena. And we cannot wait for 20 years. It has to be done soon. Okay? Argentina is a good example of that. An idiot is a president.
Can I say something?
Yes, you can.
Sorry. No, I have my
Okay.
sorry. Maybe I can bring a new ingredient to the discussion. It's almost lunchtime, but very quickly. So I can bring the view of a European educated in Europe. Until my PhD, I was living in Italy, to what I see of the Brazilian system, of course. I don't know anything about other Latin American countries. So in Brazil, I've been teaching in two different universities, here in São Paulo and in Natal, in the north of Brazil. And the common trend that I found is that the students, the youngest students I see, they are 22-ish, they are at the beginning of their master. And they don't know how to explain the ideas. So the first time I asked them to explain me something, they turned their back to me and they went to the blackboard and said, stop, 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 what are you doing? I asked you something, look at me, look into my eyes and explain to me. And they froze. Of course, not all of them, but good 80% of them. And then I really didn't understand what was going on. So I asked somebody to explain me something, and they turned to the blackboard. What's going on? And then I asked my Brazilian non-physicist friends, and they told me, oh, but are you crazy? Are you really asking them to explain you things in front of you? They wouldn't do it. I said, why not? I was really, it was unexplained. And then all the my Brazilian friends told me, well, at school we are not taught how to explain things in words. We do exercises, we write things on the blackboard, but we don't do oral exams. And then I was completely appalled. They said, okay, but then when I get them at 23, it's gone. I mean, it's too late. I mean, they don't learn at 23 if they don't learn this at school. I mean, this is a huge, I mean, the problem of scientific education in Latin America is a huge problem. There's no simple solution. But I just wanted to take my experience towards this one little element of this huge problem, this huge picture, that my education in Italy, since I was 6, I have to do oral presentation. And that's the thing, how your brain starts to work, makes connection and things. And I mean, I don't think that Brazilian students are dumber than Italian students. They're just not taught how to explain things, how to make connection. And again, I try to teach them when they're 23 or older, I think it's too late. I mean, this is a simple thing that could be changed very simple. Of course, it's not the solution, but it's the thing that struck me immediately as the biggest difference between the education I had in Italy 30 years ago and here.
Hungry, so people are hungry. So let's thank the panelists, of course. You should have restaurants in your bag, but you can follow people if you want. So, possible. I don't think we will lock it.
So we finish sharp on time. So the first keynote speaker of this afternoon session is William Bialek. Couple of 30 seconds just to introduce, and then we'll listen to the interesting topic. He's got his PhD in 83, grew up in California. He got a PhD in 83 in biophysics from the University of California at Berkeley. So after the usual postdoc tour, then he became a faculty in Berkeley already in 86. Then in the late 90s, moved to the newly formed NEC Research Institute, which is now NEC Laboratories in Princeton, where is now, now is John Archibald Wheeler Battelle Professor in Physics and a member of the multidisciplinary Lewis Sigler Institute of Integrative Genomics at Princeton University. So he also served as visiting presidential professor of physics at the Graduate Center, City University of New York, where he's helping to launch an initiative for the theoretical sciences, but he's also helping us as a member of ICTP-SAIFR Scientific Council and International Search Committee. So about physics, he's actually biophysics. He's broadly interested in laying the interface between physics and biology, and basically working in the direction of understanding how biological system works and to quantify its functionality in a way that physicists do and usually apply to physical systems. But without further ado, please.
Good, something should be green, I guess. Thank you, it's a pleasure to be here. I've made several visits to SAIFR over the years, and it's always been fantastic. So it's nice to help celebrate. I feel a little funny about this talk because on the one hand, it feels like I'm supposed to give some general survey or something, but I'm not so old that I only give general surveys, so I feel I have to say something substantive at least in the second half of the talk. So there'll be some balance. Maybe it's not as broad as it could be, but. So one of the lessons of the history of physics is that when you see qualitatively striking phenomena, they often have deep theoretical explanations. Now, sometimes it takes you a moment to realize that the phenomena are qualitatively striking. For example, the fact that the sky gets dark at night is actually surprising, and thereby hangs a tail, as we say, or the solidity of everyday objects. But there's no question that the living world sort of gives you endless examples of beautiful and surprising phenomena. And so the question as physicists is what's underneath that? Is there something deep that can be said? Or is it just a kind of amusing catalog? And so maybe the best way to do this is I'm going to focus for the talk on one phenomenon rather than giving you some broad survey. And the example is embryonic development. So I think you all know that big complicated organisms like us, or even medium-sized organisms like a fly, actually there's nothing here that indicates that it's a fly we're talking about. I'll come back to that in just a moment. All multicellular organisms start as one cell, a fertilized egg. And then, the one cell becomes two becomes four, and so on. And there's some period in which these cells are essentially undifferentiated from each other and all identical. And then magic happens, and you end up building a body with complicated structure. Actually, remember on another anniversary occasion, we were in Santa Barbara for the 25th anniversary of the KITP. And David had a list of problems everybody should work on for the next 25 years. And one of the problems that was phrased was, here is the DNA sequence of an organism, draw the organism. And, that, it's, actually, you could say before you do that, is this an organism? Which might even be harder. You'll be shocked to learn I'm not going to solve this problem for you. So let's do something a little simpler. Let's focus not on the entire organism, but on a very simple feature of many organisms, which is that their bodies come in segments. Now that's true for us too, if you think about your backbone. This is the larval form of what will eventually become a rather beautiful moth. This is the larval form of what will become a fruit fly. These things are called maggots, and they have a kind of bad reputation because we associate them with rotting flesh. You shouldn't let that bother you. This is actually a fruit fly, so it doesn't normally eat rotting flesh. It eats fruit. And you'll notice that although it's not as pretty as in the future moth, you can see this segmented body plan. And if you fix this thing and do a little bit of chemistry, you can clear out some of the sort of skin-like stuff, and it's even clearer that the body is segmented. So you might ask yourself, how does what started as one cell know to draw lines and make segments? So the answer is quite extraordinary, actually. 3 hours after the egg is laid, if you know which molecules to look for, you find that there are molecules whose concentration, as you go along the length of the embryo, and these have been lined up, they come in striped patterns. And so here, there are 3 different ones, and you see the stripes interdigitate. And if you look closely, you can convince yourself that the stripes actually line up with the segments. So 3 hours after the egg is laid, cells know where they're supposed to go in this striped pattern. And you might ask, okay, good, you chose these molecules out of a hat. How did you know which ones to look for? And how do these stripes appear? Well, these 3 molecules are chosen out of a set of 8 that are all identified. They each make nice striped patterns. These molecules are proteins. They're encoded by the DNA. Again, all the cells in your body have the same DNA, modulo a few difficulties. And what differentiates the cells from one another is which sequences they read out to make the proteins. So here you have a cell that decided not to read out the purple protein. Here you have one who did. They form this nice striped pattern. What controls whether these things are read out or not? The answer is there are other proteins which bind the DNA and turn the reading on and off. Those proteins are these 4, which also turn each other on and off in some complicated network. And how do these things know to make the spatial patterns that they do? Well, they're input molecules that are provided by the mother when she makes the egg. So there's this cascade from 3 maternal input molecules all the way through to these striped patterns, which basically provides the blueprint for making the segmented body plan. And this was all clear by the turn of the century. So this is a nice story, but what's the problem? The problem is that if you say, well, instead of saying all those words, I'd like to write down equations that describe this process. See if I can really get it right. But you know, there are 3 inputs, and those inputs can each affect all 4 of those genes. But they're all interacting with each other. And so if you try to draw this picture with circles and arrows, then you discover that there are 28 arrows at least. And when you draw an arrow, what you mean is that one molecule turns on or off the other one. And so there's a characteristic scale of concentration on which that happens. That's one parameter. And there's some measure of sensitivity. That's another parameter. So every time you draw an arrow, there's 2 parameters sitting in the background. So that means that to describe this little 3 hours in the life of this fly, you need 56 parameters. Now, this makes many of us very nervous. And I think that that culture is probably shared in the room, so I don't need to explain. However, it is worth remembering that in physics we do have models that have parameters. I can make a little poke at my friends in other fields. But you know, let's be fair, for 18 you get everything, whereas here you need 56 just for 3 hours of the life of a fly. On the other hand, let's be serious, right? Many of the places where even here, when you actually compare theory and experiment, there are things that happen which are essentially parameter-free, right? So this is true, but doesn't quite capture. And the fact that some of our theories are nearly parameter-free, I've often tried to explain this to general audiences, and I find myself struggling. You know, you want to come up with, you know, you think about predicting critical exponents or some very exotic example, but you don't need to pick an exotic example. as you all know, you get most of this structure by knowing one parameter. And actually, if you only want to get the part up here, it's important that that parameter is small, but you don't really need to know its exact value. Down here, the fine structure constant, right? Just to be sure everybody's on the same page. You don't actually, down here you need to know the actual value. Up here it hardly matters at all. So in fact, all the rules, and of course you also get the rules of chemical bonding, right? So our physicists' understanding of chemistry, which of course the chemists might criticize, is an essentially parameter-free understanding. So what should we do? And I would argue that the physicists' engagement with the phenomena of life can sort of be characterized by how you respond to this proliferation of parameters. And this is a little bit cartoonish and is meant in the spirit of giving a general introduction as opposed to telling you something in detail, but let's try. So there are various reactions. One is expecting to have a theory of these phenomena the way we have theories of phenomena in the rest of physics was just overambitious, too complicated, experiments are messy, don't try. Try to make theories that are simplified, that give you something that's kind of like the real phenomenon, but don't expect to put theory and experiment on the same graph and have a quantitative comparison. And if the experiments were messy, that would really be all you could do. I hope you'll see that experiments are not that messy. This view persists, but I think is losing ground. Another view is to say, well, there really are that many parameters, and you kind of have to deal with it, and that raises its own interesting theoretical questions. And once upon a time, that might have seemed like giving up, but of course, in the era of neural networks, maybe that's not giving up. So maybe our prejudice is just the usefulness of our prejudice has come to its end. That's a possibility. The other idea is, well, the reason that you got stuck was because you wanted a theory of what this thing looks like now, and that's asking too much. History is very important, so what you really want is a theory of how successive generations or different organisms are related to each other. And there have been important contributions of physicists in understanding that you can have universalities in evolutionary dynamics even though the particular trajectories are highly variable. Another observation, which has been useful in many contexts, is that the things that you actually care about are relatively macroscopic. They happen on the scale of microns and above, whereas all the complexity we're talking about is on the molecular scale, sort of nanometers. And so maybe, like in examples that we understand in condensed matter physics, as we zoom out from the microscopic to the macroscopic, things will actually simplify. Although there aren't very many examples where one knows how to do this calculation for problems of the complexity that we're talking about here. Finally, there's one more possibility, which is that these parameters are not arbitrary. They've been selected by evolution. And in particular, there's functional behaviors that you have to get right in order to be a surviving organism. And that constraint is very, very strong. And in the interest of getting to the end of the talk, that's the one I'm going to focus on. So the first thing that happens in the embryo, so the embryo is 0.5 millimeter long. What's happened here is that the embryo is live, obviously, it's moving around, and the microscope has been focused on the middle plane, right? And you see this invagination that happens here. This is called the cephalic furrow, and that's because this part of the body is going to be, this part of the embryo is going to become the head, and the rest is going to become the rest of the body. And that's the first macroscopic thing that you see. If you line up 100 eggs laid by the same mother, what you discover is that that cephalic furrow is always in the same position with an accuracy of about 1%. And if you count, there are fewer than 100 cells along the row here on one side. And so what that means is that cell number 33 knows that it should, cell number 32 knows it should be part of the head. Cell number 33 knows it's supposed to be part of the rest of the body every time. Can't get more accurate than that. So where does all this information come from? And the reason that this is an interesting question is that all of the molecules that supposedly transmit this information to the cells are all present at very low concentrations. They're present in concentrations which are measured in tens of molecules per cubic micron. And remember, the nucleus of a cell is a few microns across. So there isn't much signal to work with, and yet somehow you can squeeze all this information out. So how does it do it? Well, we spent a long time picking at various parts of the problem, basically to motivate the idea that things are so precise that maybe you should explore an optimization principle in which what you say is the system has been chosen, has been selected by evolution to push as much information about where the cell is through this network with the constraint that there's a very limited number of molecules. So how do you do that problem? Well, you start with the baby version, which is you have one molecule controlling another molecule, and you ask yourself, well, what can I do to maximize how much information gets from here to there? And as I said, when you draw this arrow, you really have some picture in mind where as the concentration of one molecule goes up, it turns on the other one. And there's noise, which of course is essential because that's what sets the characteristic scale of how much information you can push through. This noise has two components. One is that the molecule whose concentration is on the x-axis has to show up at some particular place in order to do its thing, and it gets there by diffusion, so that's a random process and it's noisy. And then the molecules that you're making, when you do things on a molecular scale, each individual discrete event is random. So there's noise at the input, if you will, and noise at the output. And what's important about this is that if you spend some time thinking about the physics of both of these processes, you can get a picture for what the noise is like, whose functional form doesn't add any more parameters, and whose scale is determined by the number of molecules. So that means that you can ask, how would I change the parameters of this sensitivity and half maximal concentration to maximize how much information I push through the system, given that I have some maximum concentration of this input molecule? And that's a problem we solved more than a decade ago. And then we tried to break off other pieces of the problem. You know, one molecule talks to several molecules, the molecules are allowed to talk to each other. It gets very baroque, and it takes lots of pieces, but somehow you're always solving the pieces separately. And so recently, we had kind of a breakthrough, and it became possible to actually solve the whole problem. So let's take a moderately realistic model of these four proteins that turn each other on and off. They get inputs from three other molecules. The molecules can diffuse from one nucleus to the other. They can decay. Many of these parameters have been measured, but the parameters sort of inside this network are not known. And as I said, there's 56 of them. So let's see if we can simulate this process and find the parameters that optimize how much information is being transmitted. So you might think that what you do is you choose parameters, you simulate the noisy dynamics, you do it many times, you now have lots of samples from the probability distribution of how many molecules there are at each point. And from this, you can compute the information, and now you adjust the parameters. This is a disaster because you need lots of samples, and you'd have to run the stochastic dynamics many times, and then you have to do that for every parameter setting. Don't do that. So instead, you take a cue from the real system in which the noise level is actually quite small, you linearize the equations, you get closed equations for the second moments, the distributions are approximately Gaussian and so on, so you inject a little bit of pen and paper theory into this, and now you can actually do the simulation. And so if you choose your parameters at random, you find that as a function of position along the embryo, most of the molecules are either off or on, and there's no information. If you fiddle with the parameters a little bit, you can eventually discover one where one of them turns on and off, and it tells you, front half, back half. Fiddle some more, and two more molecules figure out how to turn on and off. Again, you're wandering around in this 56-dimensional parameter space, doing something a bit like simulated annealing. Eventually, all the proteins learn to be on and off, and finally, things get fine-tuned into a spatial pattern which looks rather a lot like the real pattern, and the actual amount of information that's being transmitted is the amount of information that's contained in the real patterns. So the optimum that we find looks a lot like the real system, and what's striking is you actually can't, you might say, well, suppose you took the model and tried to fit it to the data, determining all 56 parameters, you actually don't get any closer. It's a little more subtle than that. If you optimize the information transmission, you get something that fits quite well. If you try to minimize chi-squared in the class of models, you get rather low information, and it's also a little bit noisy. So in fact, our optimization procedure gets you closer to the real thing than taking the parameters seriously as things to be fit, which is quite striking. You end up with some structure, and that structure says that there should be some interactions and not others, and that agrees with experiment. The patterns that you make, which you read out at some, as I said, 3 hours after the egg is laid, are temporally stable, which we didn't ask for, but comes out that way, and is also a feature of the real patterns. If you want to, you can even think that the diffusion constant is a parameter you should optimize, and there's a broad optimum near the, at the experimental value. And you can explore models, for example, that have 3 genes instead of 4 genes. And perhaps more importantly, you find that the landscape for optimization has an interesting structure. There are other local optima which differ, for instance, in how many molecules they use on average instead of the maximum. And they also have sort of permutations among the roles of these different genes, which remind you of what you see in closely related species, which, if we could really get that right, would be quite extraordinary. So what have we shown? I tried to introduce this by saying that there are experiments that motivate a theoretical principle, that you squeeze as much information out as possible with a limited number of molecules. What we've now been able to do is use this principle in moderately realistic complex models, and we end up with things that look as much like the real network as possible. We know we're leaving things out, and the landscape for optimization is very complicated and interesting. So I hope that this very quick tour has given you a sense for the kind of thing that many of us are trying to do, and then one particular example. And I want to end with the observation that, building a field, the physicist's engagement with biology has changed over the last generation. And this is a multi-generational project, so the important thing, of course, is that there are lots of young people who come through, and I could pick out which ones were responsible for which of the things I talked about, but maybe I'll just leave this, which I certainly find inspiring to look at. So thank you.
Hi, thank you, that was great. Question, is there a chance to kind of introduce a perturbation in the system so that now it's not kind of number 32, the one that tries to form the head, but it's changed to number 50?
So, so 2 answers. Well, oh yes, sorry. Rather elementary piece of physics that I missed. So yes, all of the molecules that appear in this discussion are encoded by genes that were identified because when there are mutations in those genes, something about this pattern changes. And so one of the things you can do is go in, now you can introduce those mutations where you want, and so you can manipulate things. For example, you can start knocking out 1 or 2 of the 3 maternal inputs. That's in some sense the simplest thing to do. And for instance, if you think that the stripes are drawn by mechanisms that are themselves the optimal readout of the patterns that we were talking about, then you have predictions for what should happen in those mutants, and those are all correct.
Okay, I have just a couple questions just to put them together. First of all, if you make something optimal, is that system robust? And second, is this the only possible answer for the problem? Could I have sort of a very active process with some error correction mechanisms, and I don't have to take the maximum information out of my system?
Okay, so let me do the error correction. Let me give you a qualitative answer to the error correction one first. We had a student who had been working on parts of this, and he gave a talk in front of a rather ferocious audience. Some of you will know the names of the people in the audience, but I'll leave them out for the story. And they said, and somebody raised his hand and said, this is all very nice, but you can have mutations in the early part, and some of the embryos hatch and produce perfectly normal looking flies. And so this sort of put a hush over the audience. And so the argument was, well, you don't need all this information because you can fix it. And he did his best, being a young student. And then our colleague, Eric Wieschaus, who shared the Nobel Prize for finding a lot of these molecules, said, I hate it when people say this. They always leave out one important point. Something like 1/4 of the embryos survive. And yes, Those are normal. But 1/4 of them survived, which means that if you don't get it right first, you suffer a factor of 4 decrease in your fitness. And so there are no flies out there who don't get it right, right? I agree that it is true that the fact that you can recover is quite remarkable, and that's worth thinking about. But that's not the core of how development works. Development gets it right the first time. The other question is about robustness. The system's not robust because every single one of these molecules was identified by a point mutation. You make a point mutation in any single one of the, if you knock out any one of these molecules, the pattern changes. So it's not robust in that sense. So that's a different question. And that's a question about the nature of the landscape for evolution. And so one of the things we don't think that our optimization algorithm is simulating evolutionary dynamics. That's asking too much. But for example, what you could do is to say, suppose you had only 3 of these genes instead of 4. You do your best. Now you add another one. Can you find your way to this optimum? And the answer is yes, you can. And by the way, 3 does not give you as much information as 4, even if you correct for how many molecules you've got, so be careful. And quite generally, what we're finding in this and other problems is that the landscape is what has some of the features of what Jim Sethna and his colleagues referred to as sloppy. So there are certain directions in which if you change that combination of parameters, it makes a big difference. And there are other directions which are very, very soft. And so that means that you can imagine navigating the landscape in ways that weren't what you thought of when you first imagined this problem. And of course, this is also a very important lesson in modern neural networks, that the landscape has these very soft directions. You have multiple optima which are connected through those soft directions and so on. So I think, I don't know whether that's robustness, because I never got anybody to tell me what robustness meant. But yes, I think the landscape is vastly more navigable than we might have imagined when we started. And now we can actually explore, right? Because we have a quantitative structure.
Hi, thanks for the talk. I'm not in biology, so maybe my question is...
It's okay, neither am I.
I'm curious about these maternal molecules. How are they produced, and how do they know how to activate these other molecules?
So let me give you the simplest example. There's one molecule where the mother places, so you remember information is encoded in your DNA, that's transcribed to make messenger RNA, and then that's, as described, as translated to make the protein. I think the images you get from transcription and translation are maybe not the right images, but that's the language. So what the mother does is she lets the process go through transcription. So now she has the messenger RNA for one of these proteins. And she sticks it down at the end of the embryo that's going to become the head. When the egg is laid, translation begins. And so now you have a box, which is the embryo, and you have a source of molecules at one end, and they can diffuse through the embryo and they decay in the process. And so you end up with a spatial profile, which is actually, if the equations were really the ones that go with the words I just said, it should be exponential if it comes to steady state, and that actually is a pretty good approximation to the data, so this is maybe not crazy. And so that's how one of them works. And then, there's one on the other side that works more or less the same way, but is a little more complicated. But that's the idea. So you basically, the mother can't impose an arbitrary spatial profile, but she can localize a source. And that's what does it.
Okay, so let's thank William again. While we set up the next talk, I can probably introduce Gabriela González, who is the next keynote speaker. So we move from micron to megaparsec, over 20 order of magnitudes change in scale. So Gabriela grew up in Cordoba, not too far from here, less than 3,000 kilometers in Argentina. But she crossed almost all of the American continent to do his PhD in Syracuse. where she got it in '95. So after the usual postdoc tour, MIT, Pennsylvania State University, then she moved to Louisiana State University, where she got a faculty position, and where she's still now as Boyd Professor of Physics. So she is helping us because she's also a member of the ICTP-SAIFR Scientific Council. And about her scientific research, scientific interest, I mean, she's working in experimental detection of gravitational waves, like the one you might have heard about detected by the LIGO Livingstone Observatory. She's one of the founding members of the LIGO Scientific Collaboration. She has participated intensely and immensely in the commissioning of the LIGO detector since 2001, since well before the detection, actually. One of the reasons why the detection was possible. After occupying various leadership positions in LIGO Scientific Collaboration that I cannot summarize, let me just pick one. She has been spokesperson of the LIGO Scientific Collaboration between 2011 and 2019, not just any year. Please.
Thank you. Okay, so there's a lot to talk about gravitational wave astronomy, so I tried to just give you a global picture and leave time for questions. Hopefully there will be many questions. If I can make this work. Yes? Yes? Come on. See, I can make a laser interferometer work, but
That's easy.
well, not the laser pointer. No, there it is. Okay, so first, let me tell you a little bit about sources. We call this gravitational wave astronomy rather than gravitational wave physics, because we are thinking about gravitational waves produced by astrophysical events. Mostly binary black hole mergers, neutron star mergers, things like that. And there is a whole spectrum, just like the electromagnetic spectrum, that if you are thinking just about black holes, depends on the size of the black holes that are merging. The larger the black holes, the lower the frequency they will, the gravitational waves that will be produced, because the black holes are going to merge at a larger distance. So the orbiting frequency is going to be lower. So massive black holes and supermassive black holes, which is what people always think first, well, not physicists, but normal people, those are at the center of galaxies. Those are very low frequency gravitational waves, millihertz or even lower. So those are here, but there are also the stellar mass black holes, the ones that are produced by supernova explosions. Those are here with frequencies of 100 hertz or so. So you need different instruments to detect these gravitational waves. And as we always say when we give public talks, Einstein did the first calculations for gravitational waves produced by his theory, and the fact that you have Newton's constant and the speed of light to the 4th power in the formula means that the gravitational waves are really negligibly small, very difficult to detect. But that doesn't stop experimentalists. So there are instruments that are measuring these gravitational waves as we speak. And at the low frequency end, let me leave cosmology aside, apologizing for cosmologists here. So those are early universe gravitational waves, but for gravitational waves from astrophysical events like black holes, for the lowest frequency ones, the supermassive black holes, there is pulsar timing that is using the radio signals from pulsars in the galaxy to measure differences in phase of the signals arriving from the different pulses. So what we are thinking here is that the gravitational wave is producing a disturbance of the space-time, which is a fancy way of saying distances and clocks is what pulsar timing, these very precise pulses are measuring. So that's the way that is being measured. This is pulsar timing experiments. For massive black holes and white dwarfs in our galaxy, there's a space interferometer called LISA that would have 3 satellites with lasers, so you measure with lasers a distance between the satellites. The satellites would be 1.5 million kilometers away, 2.5 million kilometers away. So that's LISA, and then there are the ground-based interferometers, which are the ones I'm going to talk about. There are several of these, and these are ground-based, so they are on Earth, but they are still very long. They are 3 or 4 kilometers on the side. Again, these function as interferometers. And what we are measuring in here are differences in this length compared to this length at 100 hertz of about 10 to the minus 20 meters. Meters. Remember, the size of a proton is 10 to the minus 18 meters. So you might say this is magic, but as you know, this has happened already, and not just in LIGO. You might have heard, I hope you have heard, last year there were announcements from the several different pulsar timing collaborations. This is the North American one. This is the Australian one, the European in collaboration with the Indian. This is the Chinese pulsar timing collaborations. They all publish these papers about the cosmic hum. So they are not measuring the individual signals of these supermassive black holes, but the stochastic background that they all produce together. At least that's a hypothesis. Of course, it's a very weak signal, but it grows with time. And they sing it. So let me see if I hope this works. That's why we call this the music of the universe. We sing gravitational waves. That's some members of the nanograph collaboration. All this takes patience. This was 15 years of data collection. And like I said, the signal is going to get stronger with time because in a stochastic background, you can integrate the same signal with time. So that was so exciting. And there again. There's also news with LISA. LISA is a project that led by the European Space Agency, but collaboration with NASA and other agencies from other countries. And January 25th, so just less than a month ago, they finally really gave the final approval for the launching of LISA in 2035. Like I said, this all takes a lot of patience, but it's happening. And it's a mission that's going to have signals of exquisite signal-to-noise ratio and lots of different kinds of signals. It's going to be amazing, but we have to work and wait for it. But about ground-based observatories, that's what I wanted to tell you about. And Ricardo mentioned LIGO. LIGO is a collaboration that started in the US with 2 observatories. Then it became an international collaboration with technology that was also adapted from, that was developed by many different countries around the world. So this is not a US project now, it's an international project, but the 2 detectors are 4 kilometers long in Louisiana and Washington State. We have been taking data with Virgo, which is a 3-kilometer detector in Italy, which is managed by the Virgo collaboration, which is also an international collaboration and not just in Europe. There is a Kagra detector, a 3-kilometer underground detector in Japan, and they finished constructing it a year and a half ago. They began operating last year with not much sensitivity. Unfortunately, January 1st this year, there was an earthquake, and it didn't break it, but it broke lots of parts of the detector, so they are now undergoing reparations for it. But they are part of the network. And India just approved also last year the funding for a 4-kilometer detector in LIGO India. There's even a cat drawing in there. So I had this picture, this map for a long time, and now I had to change it because Kagra is now commissioning, not just under construction, and India is not just planned, it's under construction. So things are happening. Take many years, but they happen. And talking about collaboration, this is the map of the institutions in the LIGO scientific collaboration. We do have where is, we do have a nice Humans of LIGO. We have a page called Humans of LIGO, but I didn't think about putting it like that. It's a beautiful way of acknowledging the diversity of people in here. This is the LIGO scientific collaboration. Like I said, we collaborate with Virgo and with CAGRA, but these are all part of the LIGO scientific collaboration, and you can see Ricardo there. That's now there are two groups, right? But ICTP is one, and there are some new groups in Latin America. There was one in Argentina, there's one in Colombia, and there's Colombia or Venezuela, or both. Colombia, yes. And there's one now in Mexico. We incorporate groups every few months. Okay. You probably remember this. It wasn't that long ago, 2000, well, it wasn't 20,000, it was 2015, when we discovered the first gravitational wave. These are the signals in those photodetectors in Hanford and Livingston on top of each other. These are time frequency diagrams that we love. And those were from parameter estimation of this. We knew it was an event produced by the merger of two big black holes, 30-mass black holes, that happened not in 2015, but 1,000 million years before. You probably also remember 2 years later, in August 17, we measured the merger of two neutron stars, and that was amazing, not just because we measured, this is a time frequency diagram, we measured the gravitational wave signal with LIGO, with the two LIGO detectors and Virgo, so we could triangulate for the first time with not just this signal, but several others, and tell where it was coming from. And it was coincident with a signal in the Fermi satellite that was consistent in localization and in time. This signal in the Fermi satellite was only a couple of seconds after the one that we had measured in LIGO and Virgo. And then there was all telescopes in the world were looking in there and finding signals in the X-rays, in the radio. These are gamma rays in the whole electromagnetic spectrum. This is now one of the best studied phenomena in astronomy. So these are old news. Let me show you the timeline when this happened. People began thinking about these detectors in the 70s. The project was approved in the early 90s. That's when I was a graduate student doing my PhD, excited about this. That was just starting, but it was 2015, 2010 when the second generation of LIGO detectors that we call advanced LIGO detectors, those were approved in 2010, and it was 2015 when we discovered the first gravitational wave there. This was the first observing run, and these numbers, without going into a lot of detail, these numbers measure the sensitivity of the detector. It's the average distance to which we can see binary neutron star mergers, so the larger the number, the better. The advanced LIGO expected sensitivity, if we had everything working, was going to be around 170 megaparsecs. And we started at about half of that. So we had a lot of work to do. We stopped improved sensitivity to about 100. We took data with Virgo, and we measured this beautiful neutron star merger. We stopped, we improved the sensitivity, we took data, even with CAGRA a little bit. We were planning to stop there, but a pandemic made everything stop, including us, and made progress a lot slower in this gap. But we began taking data again in May of last year, and this is a present now. We are going to take data for another 9 months or so. With Virgo, we have not been taking data with Virgo here. We have another gap, and then we have the future. Notice that this is 2030. We plan in terms of years, not just months. And you can see all of this. This is posted and updated every few months. Now, this is a catalog that we had from these first 3 science runs from before COVID. And there were 90, we published 90 detections. So you might remember The first one, the neutron-star merger, you might have thought, well, there were a few more too. There were a lot more. There were 90 detections. That was the first one. That was a binary neutron-star merger. This plot has some chronological order, so it's kind of timing here, but it's not to scale. And then this is the solar masses of the individual black holes before the merger and the final black hole after the merger. So that was the first one. We had 3 signals in the first observing run. We had 7 more black hole mergers in the second observing run, plus this beautiful neutron-star merger. And this is what we had in all of 0103. And you can see that we have a lot, not just the 2 famous ones. So let me just highlight a few ones, and I'm not going to give details, but I can give you more details if you have questions about those. This is the largest one we measured. That the total mass was 150 solar masses. The ones that made that merger, the ones in here, are so big that astronomers don't think that they could have been produced by a supernova explosion. So this might be a second generation merger. Maybe this one, especially the larger one, was already a merger of 2 other black holes. And by the way, I don't know if you know this, but let me tell you, let me remind you that before our first detection and before these detections, there was nothing in physics or astronomy that forbid that there were mergers of black holes, but nobody had seen one, because if you have 2 black holes, there's nothing to see. But it was not, some theories, some population theories predicted that there would be none, because they took too long to get together and merge, so there wouldn't be mergers. And here we are, knowing a lot more about the universe with these new detectors. These are neutron-star, let me see, this is another binary neutron-star merger that actually has a record in the total mass of the system. These are neutron-star black hole mergers, so a neutron-star and a black hole. So we have one of each kind. We even have some in which the mass of one of the objects is somewhere in between a neutron star or a black hole. We cannot detect from our measurements what they are, because we don't have the details of the merger that would tell us the difference between tidal deformation for a neutron star or an event horizon. So this is the timeline I was telling you. We started taking data in May. And this is that number I was telling you about our sensitivity. This was the last part of 03, and I scaled this with PowerPoint magic so that the scale is more or less the same. This is 04A, the first part of 04. This is the second part of 03. This is the range for Livingston, which was a bit better than for Hanford, and both of these were a bit better than Virgo. In 04, both detectors were better and improving, and they are now at about 160 megaparsecs with lots of different technologies that I can speak hours about. We have been posting public alerts, so if you go to gracedb.ligo.org, here, you can tell all the alerts we have had. You can subscribe in here. And we have had, it says here, 81 total alerts. So we had 90 before we started 04. Now we have at least 81 more, of course, with offline analysis. Some of these could go away. That rarely happens, but some more will be visible with deeper analysis. For each one of those, we have a localization and a probability of it being a binary black hole or a neutron star merger. And all of those 81 are most likely black hole mergers, except for 2, one that is maybe a neutron star black hole, and another one that might be binary neutron star, although it's most likely a neutron star black hole. So one of the things we are learning is that there aren't as many neutron stars as we actually wanted, at least. We are still not clashing with any other prediction. So this is the current landscape. It's very exciting, not just with us, but at all scales, even this CMB, this is measuring the early universe gravitational waves by looking at the polarization of the cosmic microwave background. So you measure microwaves, you look at the polarization. That polarization was affected by the gravitational waves in the early universe. So that will happen, but might take a little bit more time. Those are very sensitive CMB experiments, but this is all happening. We are all building these instruments, improving these with time and with better data quality. We are improving the sensitivity of these. We are even thinking about third-generation detectors. We call these second-generation detectors, so we are already thinking about the next decade. There's a lot happening, and I hope you have questions. Thank you.
Thanks, Gabriela, for this inspiring talk. I'd like to ask you if what is your take on opportunities and lessons for the quantum sensing community on gravitational waves? I know Advanced LIGO is already running with squeezed states, but what else do you foresee in that direction?
What lessons we have in science or in politics or in collaboration? We have many lessons learned.
Yeah, perhaps in collaborations, like, I mean, this is perhaps the most impactful example of where using quantum states of light can enable another level of sensitivity and suppressing noise sources and so on. So what do you see there?
Yes, actually, well, you're talking about collaborations on the technology development, and yes, we are using squeezed states and very sophisticated squeezed states because they have different, we are squeezing the vacuum, if that sounds more magic than detecting gravitational waves. In an interferometer, we make the two beams that come out of the interferometer having destructive interference. So what we are measuring is vacuum. That vacuum has a noise, which is, in the best case, coherent, the noise of a coherent state, which is limited by Planck's limit. In the noise in amplitude times the noise in phase has to be larger than Planck's limit. And we were squeezing already in 03 the noise in phase, which helps us at higher frequencies for detecting, well, having better sensitivity. We are now squeezing at lower frequencies in amplitude and at higher frequencies in phase. We call that frequency-dependent squeezing. I have to say that this was a lot of learning from the quantum optical community, but this was developed mostly in gravitational wave groups, which then brought it to quantum optics, and now it's very, very exciting from both sides. On collaborations, collaboration of collaborations, I have to say that this is the best example. If we had been competitive and not taking data together, we would have missed this event. There would have been no electromagnetic counterparts. And because we were sharing the data live, and announcing it to astronomers, is that we have such a beautiful physics and astrophysics from there.
Well, I think you are talking about the classical gravitational waves. About the gravitons, don't you have any comment about the gravitons, maybe, or classical gravitational waves?
Well, gravitons are particles in the particle version of gravitational waves, but if you look at the energies we are looking at, even though the displacements that we are measuring are so incredibly small, they are produced by billions of gravitons. So we are not looking at effects of gravitons individual. We are looking at the collective action, which is the classical picture of gravitational waves.
So I must understand that there is no graviton in this context.
there's no evidence of quantum mechanics of the gravitational field that we are sensitive to. Of course, we have upper limit experiments that might help with other things, but no, we are looking at the classical regime of gravitational waves.
Classical waves. Thank you very much.
Yeah, Gabriela here. Thank you for this cool talk. From the theory perspective, I mean, I'm looking at how to think about gravitational waves that comes from phase transitions, which are tough because are in the Hertz region, but kind of if you push it a bit higher frequencies, then it go too low in amplitude, so to say. So have you thought about how to I mean, what is your projection in the future to try to think about moving in frequencies and moving down in your omega gravitational wave, whatever it is that you call it, so that maybe ideas of first order phase transition gravitational waves could be at reach, which could be super cool for many ideas of matter-antimatter symmetry, for example.
Yes. And I have to say that we not only look for mergers of neutron stars and black holes, we also look for unmodeled bursts of gravitational waves that could be produced by phase transitions, by cosmic strings, by many of these things. Even the experiment, the results of pulsar timing can be explained by some other sources than mergers of supermassive black holes. So we are looking for those. We have not found anything. Improving our sensitivity to push the low frequency part of this is the hardest part of the job. The one thing that we are thinking about, which is probably the best bet, is to have third generation detectors. There is a project in Europe called Einstein Telescope, one in the US called Cosmic Explorer, that are essentially 10 times longer, so you have 10 times more sensitivity, even at low frequencies. In principle. In practice, we have never achieved yet the sensitivity that we want, that we are designed to have below 30 hertz or so, because there are so many technical sources of noise in there that's why commissioning is never done. That's why we have, what is the timeline? We have these big gaps. Well, of course, there was COVID in here too, but you know, this improvement is not dramatic. It's not like you have to go and turn these bolts and now you have 20 more megaparsecs. I mean, every megaparsec we have with this metric, it's nights and nights and nights of work. And I say nights because nights are usually better than days, but.
Okay, thank you.
Okay, last question.
Thank you. Do we have indications that we missed some electromagnetic counterparts during the time where the detectors were turned off? Like, for instance, do we have like gamma ray burst observed by satellites that looks exactly the same as the one that was observed in 2017?
Of course, I mean, we are missing lots of gravitational waves. Once we went online for 04, we are seeing a bit more than a merger a week. So that means that we have been missing at least that many mergers in this gap. So gravitational waves are going through all the time. However, we need to have a trade-off on how long do we stay down so we can bring this number up, versus how long do we take data so we don't miss gravitational waves. And that's something that's being discussed all the time together with LIGO, Virgo, and CAGRA.
But specifically for the electromagnetic counterparts?
I know those would be the most painful to miss, but at the sensitivity that we have now, we have seen one in several years of data taking. So do we want to take data for 10 more years without changing anything, or do we want to make the detector better so that we have signals maybe once every 6 months instead of once every year?
Just a qualification, it's several years, but on real time, it's a bit over than 1 year. Because
That's
of
right.
course, you're on for 1 year.
And the sensitivities are different, but yes.
Okay, so we thank Gabriela again. And we are moving to the last speaker of this keynote speaker session. So, okay, maybe I just introduce while they set up the slides. Professor Rosario Fazio is from Sicily in Italy. He got his PhD in the 1990 at the University of Catania. So he had many positions, Scuola Normale Superiore of Pisa in Italy, School of Advanced Study in Trieste, the SIS, and the University of Naples, Federico II, from which he is on leave, and now is director of the Trieste Institute for Quantum Technologies, and he's also a member of the Italian Accademia Nazionale dei Lincei. And he's helping us, as William and Gabriela, as a member of the ICTP-SAIFR Council. So now we will move back to small distances, actually to ultra small and quantum effects. So his research line, if I can summarize into keywords, is quantum and many-body. He's working in theoretical condensed matter and quantum information processing, focusing on quantum transport in nano devices, mesoscopic, superconductivity, quantum simulators, quantum information, many-body system, and open many-body system. So now we are eager to listen to you.
So thanks a lot. So my idea was to talk about a field which is at the border or cross connection between quantum information and non-equilibrium and statistical mechanics. And I will be, I will give you a flavor of several directions that are being pursued these days, just highlighting in particular things which are of interest both for people here at SAIFR and people in Trieste. So a quantum computer may look like this. I think I took this picture from the web. I guess it's Google. Somewhere here, there are superconducting qubits, a lot of wiring. I mean, this is not the only example of how a quantum computer can operate, but this is one of the currently most successful around. But if you look at the way it works, it is rather like this. So essentially, you have a number of qubits as an input, then you apply several gates. Again, this is another picture I stole from Google. You apply several gates, and at the end, you go and measure what is the output, which hopefully will give you the solution to your problem. But in the same way, you can think to this input as a bunch of spins that you initialize in a certain way, and then you just follow the ideally unitary evolution of the system up to quite complex wave function that, properly measured, will answer will give you an answer to the problem you want to solve. But you see that if you forget about the way we start this discussion, essentially here we are looking at just evolution of a many-body system where, I mean, the fact that the system can evolve unitarily will allow you to explore several new directions. This is why, and I'm talking about things which happened in the last 2 decades, both quantum information and statistical mechanics found an area of overlap that was very influential for both disciplines. So first of all, methods of quantum information have proven to be very useful in many-body physics. I mean, nowadays it's pretty common to discuss about entanglement entropy, characterizing states, quantum states, by looking at their entanglement properties. But this is something quite new that came thanks to quantum information. In the same way, methods inspired by quantum information allowed to develop more powerful ways to simulate quantum system. I'm referring in particular to tensor network or connected to DMRG and things like this. But it's not the only thing. I mean, the influence was also in the opposite direction. Methods of statistical mechanics allow to study those circuits that I showed before. And if I have time, I will flash some example of this. Well, and probably the best way to see how these two fields, many-body and quantum information, marry is in quantum simulators, which at the end are nothing else than non-equilibrium many-body system. Last but not least, many-body physics is playing an important role in quantum technologies, and I will have a couple of examples of this sort later in the talk. I mean, this is not by any means an exhaustive summary of how things are interconnected, but just to give you some ideas on this common territory I would like to briefly describe. I mentioned quantum simulators. I mean, this idea, which we all know was originated by Feynman, was to say, well, we have to study complex many-body system or complex phenomena, then probably instead of using a classical computer, which poses some limitation, we can have a quantum system, a controllable quantum system, just to simulate the physics of some model Hamiltonian. At that time, this was kind of a dream or just a long-term vision, but since more than one decade, probably 2 decades, I mean, there are several different experimental systems which have all the qualities and all the characteristics to act as a quantum simulators. Here I just listed few of them, but essentially common to all these examples, going from ions to atoms to Rydberg or to photonics or superconducting cavities, there is one common property which is fundamental. All of this can be controlled in their dynamics. And this is something, I would say, pretty new that allows to explore new phenomena. And so essentially what you can do with all these examples, or sorry, with all these simulators is really to look at just a many-body evolution. This is something that in traditional condensed matter is not possible, just to follow the unitary evolution of many-body system. It's something that you have to have, in a certain sense, an artificial and well-protected many-body system to do so. Actually, unitary evolution is not the only thing people are looking at, in some cases, even the environment can be controlled, and can be controlled in such a way that the evolution of the open many-body dynamics is in its own properties achievable. I will say something about this probably if I have time. But let's say, as compared to the initial idea of Feynman, I would say there is, over the last years, there is much more that people have been achieved. So, first, for example, first, it is possible to study fundamental question in statistical mechanics associated to thermalization or lack of thermalization that became possible only with this type of very clean systems. And I just mentioned thermalization, but there are a lot of questions that people study, like defect formation. I mean, I'm referring to proposals by Zurek to look for defect formation from early universe to be seen in quantum simulators. But there is even more. Actually, with these quantum simulators, you can really invent new state of matters, as long as they are allowed by laws of nature. It may be possible to realize in artificially fabricated system, whereas in real, let me call it real system, they are very hard to be seen. One example is, for example, time crystal. So as I said, I will then just give you a flavor of the major problems. I mean, it's just a selection of examples, but a lot of work has been done on trying to understand how isolated thermal system can thermalize, which is essentially try to understand how a complex many-body system can act as its own environment. I mean, there were very important theoretical studies. I mean, I just mentioned eigenstate thermalization hypothesis and all the work that is connected. But thanks to the experimental realization of quantum simulator, it was possible to really explore or just to look experimentally how a many-body quantum system, this is essentially a one-dimensional interacting Bose system, can be described in its local properties through a dynamics which will converge to thermalization. This is not always the case, because there may be cases where the system can show a series of constraints in the dynamics. This is one example, integrable system. This is a one-dimensional interacting Bose system where it was possible to see, instead of this rapid thermalization, oscillations in this, like these breathing modes of going on for several hundreds of cycles, pointing out that the dynamics is very much different from this. And lack of thermalization is not something which occurs in this type of systems, but in the last years, there have been a plethora of very interesting cases that have been discovered. Many body localization, which is a kind of highly non-ergodic behavior in which it's a localized state, but in an interacting system with very peculiar properties. It does not carry, does not allow to have transport of mass, charge, whatever, but at the same time, information can propagate through the system. So you can have kind of dynamics in the entanglement, whereas properties of like energy or mass are totally frozen. More complex situations of non-ergodic behavior were found, not in the full spectrum like in MBL, but in some part of the spectrum. So systems that in large part of the spectrum shows thermal states have a bunch of eigenvalues that are highly non-thermal, which were dubbed as quantum scarce. Yes. I mean, all these experiments were done essentially by doing quenches. The same picture I show at the beginning, you just prepare the state, you evolve and see what happens. But this does not, this type of dynamics does not, is not only important to explore features of statistical mechanics, but it plays also a role in quantum technologies as, for example, this is one example, it was explored for quantum batteries, essentially devices that allow to store and eventually release, extract work. The last thing I would like to mention in the last couple of minutes is about open systems. I mean, the standard mantra of quantum information or quantum technologies is that environment is bad. And in this is true, environment is bad, but in some cases, if you are able to control or to engineer entanglement, actually, you can use it to prepare quantum states. You can also prepare it, for example, just topological states, and this is the last remark I would like to make, you can prepare states like time crystals that are states of metal predicted for the first time 10 years ago by Wilczek as states which break time translational invariants that can be realized by properly designing, I mean, this is one of the examples, but probably designing coupling to the environment. And with this, I just skip this because of lack of time and just conclude in this rapid and probably not clear presentation, I wanted to emphasize all the cross-connection between information, science, and many-body physics, and these are directions that both at ICTP and SAIFR, we have many people involved, and last year we organized a school on this. Thank you very much for the attention.
there is no question, maybe. Okay, one up here.
You didn't mention the frontier of this, which are the topological qubits.
No.
Why not?
No reasons. So it's...
well, okay, I understand the things that we have are these things which are very
So there is
noisy
there is, well, so let me say, topological qubits are still not, I mean, theoretically are very, very interesting avenues, but experimentally they are a bit behind the other realizations.
There isn't a topological qubit yet, that is true. But
so that's why this was the reason. I would say that, for instance, something which I found a real breakthrough in the last months or so was the experiment by looking on Rydberg and surface code. That I think it will be a game
well, that's
changer.
getting close to that, essentially.
Yeah.
And many of these so-called quantum error correcting codes are essentially topological states.
Exactly, yes. So.
Well, I'm struggling to understand better what is quantum ergodicity. What is a quantum ergodic system? I know classically that ergodicity.
So the question
time
is,
ever is a limit.
Suppose that you have
system. What would be like a thing like that?
So suppose that you have a closed system that you let evolve. You want to know if locally it looks like, and you put some energy. I mean, it's prepared a given energy. You want to know if the local properties are compatible with the description in terms of a Gibbs ensemble or not.
Okay.
So locally, yes. No, it's quantum. So you want to know if locally it looks like a thermal state. I mean, to simplify things.
Okay. I then suggest that we can thank all the keynote speakers of this session. And we resume at
Okay, this is the panel on the role of theoretical institutes. We have 7 speakers. Each will speak for 3 minutes. And I will follow Eduardo's example. I have a 3-minute stopwatch. How do you make a noise at the end? What? It does automatically. Oh, but you have to set the time, right? How do you do that? Whatever. There's a way of setting that up. Oh, 3 minutes. Okay, good, got it. Okay, so each of you has 3 minutes, and then we'll have some time for questions and answers. And let me start with listing. We have 7 speakers, so I'll list 7 different roles of theoretical institutes and why they are so important. So, number 1, theoretical institutes are so important because theorists like to get together. Contrary to public perception, theorists are actually very gregarious. They really enjoy each other's company. They like to spend their time presenting their ideas, arguing, collaborating. That's how we work. It's not true of all fields and all sciences and all activities. Experimentalists, for example, like to work within their own laboratories. But theorists love to communicate, love to have the time to discuss, collaborate, and argue and collaborate, compete and cooperate. Number 2, why institutes? Well, I regard theoretical institutes, like this one, or KITP, or ICTP, et cetera, as national, international facilities. They are to theoretical sciences what national labs or international labs like Fermilab or CERN is to experiment. So, you know, you can do a lot of things in individual departments, individual universities, but to do serious work, research in experimental physics, you do need these big centers where you can put together all these expensive and facilities that many people can take advantage of. And in some sense, theoretical institutes are in that category. They should be thought of as facilities for an international community of theorists. They're open to the whole world. In that sense, they're very democratic. Not everyone can be at the top university. There are only so many top, by definition, research universities. But everybody can visit, participate in programs run in theoretical institutes like this one, for example. So they're democratic, they enhance the diversity of the talent that can contribute to theoretical physics, and that's one of their most important benefits. 3, they are the best way by far, at least in the theoretical sciences, to encourage disciplinarity, which used to be and still is, I think, somewhat of a buzzword among funding agencies and scientific societies, very difficult to achieve. But they can be achieved at institutes like this. Physics is very broad, and it's hard to define its boundaries. In fact, so, what was it, 20 years ago at this conference that Bill referred to, we celebrated 25 years of the KITP, I defined physics as physics is what physicists do. The only problem with that, which is true. So Bill, for example, this works on the development of a worm, some kind of C. elegans, was that? Yeah. And, well, that's physics, because it's what physicists do. And they use the tools and the culture that we successfully have developed over 400 years or more. So physics is a culture, in my opinion. It's not defined by this, some kind of strict, meaningless division of nature into different disciplines. Nature has no boundaries. At the time, back 20 years ago, I had to define what a physicist is. And so, somewhat of an American flavor, I must say. A physicist is somebody who learned E&M from Jackson. That was in order to remove the engineers. But what I really mean is that we all know what a physicist is. It's someone who grew up as a scientist in the physics culture. And once we have that culture, we can use it in the many different areas of nature that aren't necessarily defined as physics. But that's difficult to achieve in universities or in society at large, because both universities and society are divided by artificial, so often meaningless divisions. If a university wants to explore new directions, it actually has to hire somebody and give them tenure and make a commitment for many, many years. An institute like this, or like mine, can experiment, moving the frontiers of physics into new areas at a minor cost. We simply run a program. Okay, if it doesn't work, it fails. So what? We've lost one program. We don't have to hire somebody for 30 years. This is enormously advantageous. And it also suggests, by the way, that if that's understood by those who populate and run such institutes, that experimentation is one of the primary features of such institutes that they should take advantage of. Not always easy. That's 4. Let's see. Number 5, institutes of this type are ideal places for young scientists. Graduate students, postdocs. There's really nothing better than being we have a whole program of visiting graduate students who come for a semester. We attract some of the best in the world now, and they have a wonderful time. Same is true of postdocs. Being a postdoc at a major research university is fantastic. But what is special about these institutes is that postdocs, graduate students, young people, before they've totally committed to work in a given area, have the opportunity to learn about many other areas of research, often to switch fields, or learn about things that will benefit them in the future, even if not in the immediate present. In institutes like this, which don't have teaching responsibilities or formal roles, everyone is much more equal than they are in other situations where there's a well-defined hierarchy of student, postdoc, assistant, associate, tenured, At institutes like this, everyone is equal, first approximation. And that's enormously nice, and especially for young people, great. Number 6, as has already been evident in our previous discussion today and some of the examples that were given, institutes like this can play a very important role in outreach and education, because they cover so many different fields of science, and have so many visitors and people passing through that they truly are an ideal place to do the kind of very innovative and exciting outreach that ICTP-SAIFR does. And third and final, institutes like this are cheap. Theorists are cheap. Compared to the resources that are necessary to do modern physics in any field that involves experiment, we are so cheap. So the investment in such places, although not evident as the investment in CERN. CERN makes discoveries and makes the news. Institutes like this, we don't necessarily make immediate discoveries, but with sufficient thought and analysis, one can justify the scientific impact of these institutes way beyond the actual outlay in funds. And therefore, in some sense, institutes like this are easy to fund. Not that governments or funding agencies always realize this. But I'm very impressed with the decision of FAPESP to double the budget of this place. That's an extremely wise decision. In the grand role of things in Brazil included, I don't think that's a big part of their budget. It's probably a very small part of their budget, but its impact will be great, and they should be applauded for that. So, okay, now we're going to start, and yeah, but we have plenty of time. And start with the 3 minutes. The original, the oldest of theory institutes, the ICTP, Atish.
Okay, thanks, David. So you have taken some words away from me, since some of the points that you made is exactly what I had in mind to say, so I completely agree that a place like ICTP is a bit like the slogan I use is that it's like CERN with a blackboard. And that's why it is cheap. You don't need a big accelerator. You just need a blackboard. And it's very true that with relatively less resource, you can actually reach out to a very important part of the scientific landscape. And that, I think, is a very important contribution of the theoretical centers like ICTP. Another thing is, of course, that because theorists are cheap, that observation is certainly very important. And that was the argument, in fact, that was used for the creation of ICTP, or also institutes like Tata Institute of Fundamental Research, where I worked. So I know both these institutes very well. Because it cost a lot less than putting, let's say, a big laser facility or an experimental facility in a country like India, and you can actually go a long way with fairly low investment. So theorists are cheap, and I think without being modest, we can also say that theorists are smart. So in that, also because of their profession, they can jump across domains much more easily than an experimentalist can. I mean, once the experiments have committed themselves to some big, important project, they cannot just jump and start doing something else. So it becomes easy for a statistical physicist to start doing biophysics or do something completely different. So I think that's another big advantage. In that respect, I would say, therefore, there are less domains. They are much less constrained by the domain of their research. And this helps and theoretical physics is very international, so this is also very important for a place like SAIFR and ICTP, that internationalization is very easy to achieve in a center like this. Many times, many important initiatives like I mentioned Sesame today took place in a cafe, a bar in ICTP, where scientists from Israel and Iran could come together and talk to each other about having a synchrotron facility in Jordan. And this universality of theoretical physics and the common culture that we share together is something to be valued in the world that is more and more broken into parts. And the final point I would like to make is that I will follow the time taken by the chair. So the final point that I would like to make is that, which is I have seen in Tata Institute also, it can really be a nucleus, and I hope that becomes true also of SAIFR. It can nucleate many new directions in the country in which it is located. So Tata Institute, for example, spawned the microwave GMRT project, biology. So starting with a theoretical physics institute, it actually spread into many different areas, and so did ICTP. We went into climate. So I think it's an easier path to follow than start investing in a big radio telescope facility right away. Thank you.
Questions for Atish? We have time for one or two questions. Or we can... Speaker is Luis Herta from CLAF.
Thank you. First of all, to thank the organizers for the invitation and the possibility to share with you what CLAF has done in Latin America. I have a notes in order not to forget anything and the tyranny of time. So CLAF was born in 1962 in Rio de Janeiro. It was promoted by the CVPF, the Center for Brazilian Physics, in research in physics, and also as an initiative of UNESCO. There you see the countries that are actually in present active. That does not mean that they are they have paid their membership dues, but they are active here. And well, the model was CERN in the beginning, created less than 10 years before CLAF was created. And as in the case of CERN, UNESCO played a role. Actually, in 1950, the Nobel laureate Isidor Rabi promoted a resolution in the UNESCO Assembly that UNESCO promote this kind of regional centers for research. And CLAF was created, of course, to support the development of research in physics in Latin America, in all areas. Compared to an institution located at a place where people go to work and then come to their houses within reach of their work, CLAF was a very different challenge. Just to bring together people scattered in different countries with interests, rather focus on their scientific neighborhood, mainly dealing with the difficulties of our countries, low budget for science, also decades of strong social stability and political persecution. That was a challenge. How did we face it? First, following the original dream. The original dream was like CERN to organize and build an international laboratory. But the idea was abandoned years after. In comparison, CERN's initial budget to start the project was just about $5 million. CLAF, in the best years, its budget has been close to $500,000, but nowadays it's $100,000 every year. So it is modest budget. But also the scientific culture in the 60s in Latin America was not enough strong. So it was difficult to pursue the original dream. But I have to say that nowadays, CLAF has been very important for Latin American physics, distributing scholarships, financing specialized schools and exchange of researchers, and promoting working groups in different areas, some of them interdisciplinary nowadays. We have put nowadays our efforts in promoting the establishment of specialized units. For instance, we have an astroparticle physics unit, which is involved in the SWGO initiative, a unit on history of Latin American physics, and a unit on nanotechnology. Also a unit on renewable energies was also working in past years with a PhD program in Mexico, but recent policies of the Mexican government have not favored the continuation of the program, but we are seeing what to continue it. And also agreements with international institutions, CERN, EGI, the grid infrastructure, European grid infrastructure, the ICTP financing some scholarships to pursue studies in Latin America, and CNPq scholarships, of course. And if I want to make a summary of the present challenges, I would like to say that the main challenge is promoting multilateralism in physics. In a world where multilateralism was weakened, an organization like CLAF is important, which could commit governments to collaborate and support common goals. Every effort to facilitate the mobility of the community and students between our countries will be fruitful to position our real science in the world, and above all, convince our governments that it's worth putting energy and resources to the science and technology of our countries. Thank you.
Well, I hope you have success in convincing the state of Rio to follow the state of Sao Paulo. Any questions for Luis? Comments?
I remember that at least in the 80s, CLAF used to at least give partial support for meetings in different parts of Latin America.
Yeah.
There was a Latin American School of Physics, for instance, and CLAF used to go from one country to another. I don't know if that still exists. I don't think it does.
No, we have to recover that, I think.
This is something that CLAF supported.
Yeah, it's very, very, very important to reorganize a Latin American school in physics. But also we are supporting different events or meetings. We receive about 8 to 10 requests on that, and we put not much money, but enough to maintain this collaboration, this connection, I think. But that initiative must be recovered.
Okay, our next speaker is Alvaro Ferraz from the International Institute of Physics in Natal, which I also know very well.
Yes, and I don't have to give any justification because I just follow up what David said. Now I want to show just a few pictures of the Institute. This is our building. The mission that we have there is similar to the mission of ICTP-SAIFR. Our model to start with was really Santa Barbara. We wanted to be small. We don't want to grow to be a very large institute. But we wanted from the start to be able to promote these longer workshops, to be able to bring many visitors, to have them interact with each other, to have them to interact with the students, and a small staff. So the idea is to carry out innovative work, as we all try to do. Our what we had in mind was to be a center of excellence. This is not enough in Brazil. You have to do more. You have to be able to play some role also in society as a whole. And the reasons for that, is that, for instance, the Institute, it's funded by 2 ministries. One, Ministry of Education. The Institute is located in the Federal University of Rio Grande do Norte. It's different from UNESP, it's a state university. And we started up being supported by the Ministry of Science and Technology. And we have a committee, we have a board, scientific board. David is an important member of the board that meets every year in Natal to establish the program 1 year in advance. And they happen to be very successful in selecting very good programs and attracting very good people to go there to promote scientific events. We have, I think what is most important in such an institute is the atmosphere, the working atmosphere. People who go there, they like to be there. Natal is a very special place as well. It's a very nice city located in the northeastern coast of Brazil. It's not hot, as you can imagine, because of the proximity to equator, because we have a lot of breeze from the sea. So it's very pleasant to work there, to be there. We have many visitors program. The idea is to have a number of, this is the board, by the way. You see many people who are there on the board. Some of them are also here and are in other places. So we all communicate with each other. We all know what each other is doing in a way. And this is our research leaders. We have the addition now of Klaus Capelli, who is organizing the educational sector of the Institute. This is very important because of these connections with the Ministry of Education. So we ran last year the Olympiads for girls, young girls, for the first time in physics. This is done by mathematics for a number of years. Physics never did before. So we did that in collaboration with the Scientific Brazilian Society. We want to have this collaboration more and more with the Brazilian Physical Society. We are also running a special program with gifted gifted second-year students and from 14 to 17 years old. We are doing that in collaboration with the foundation, the Institute Principia, and also with an institute from the Federal University of Rio Grande do Norte. We did a meeting, 1-week meeting. We attracted students. The students came from São Paulo. They were very excited. They were very pleased with the activity. We want to repeat that every year. We are running now in March a program for the training of students who are going to participate in the Olympiads. This is done together with the Brazilian Physical Society. And we have these other groups, strongly correlated electronic systems, quantum information, string theory, mathematical physics, and particle and astroparticle physics. So these areas are selected by the board itself. The board, we have this, as I said, many visiting programs. These are some of the pictures of the distinguished professors who are there. They come every year for at least 1 month, and they come and they return. They are usually there for 1 month, and they interact with the students. It's very important, very lively. They like to be there. And of course, we have these programs, many conferences, and many activities, and some of the pictures of the posters are here. And I think, as David said, it's very important to have such an institute, and important for Brazil as well. So thank you.
So any questions for Alvaro? Comments, questions?
Thank you. Since you have some overlap with ICTP-SAIFR, do you have any plans to collaborate or organize some things together?
We have some collaboration. We have Pedro in our board, for instance. We used to have Nathan in our board in the very beginning. So we've been running programs in string theory together. We just had one agreement done with Saclay, with the participation with people from Natal and also Pedro and people from here. So we have good ties with the ICTP-SAIFR.
Nathan, do you want to comment on that?
Yeah. So we have, of course, had some joint activities in relation with fields that we work in. It would be great to have more. I think, as maybe people don't know, we started in high energy physics. They started in condensed matter physics. So we're slowly converging, but it's not immediate convergence.
Right. Okay, so let us now move out of Brazil, and Marcela Carena from Fermilab, who's the head of the theory division at Fermilab.
Thank you. I'm also an Argentinian, in full disclosure. So, so actually, I think there are, what is the role of physics centers is the topic. I think that physics centers can be very different, and I have been very fortunate to be part in different ways to many physics centers around the globe. Starting in Bariloche, where I studied. That's a physics center in Argentina, and many others. And I was fortunate to learn a lot from David at the KITP. I was really fortunate to come here at ICTP-SAIFR, and it was my pleasure to give my thoughts to Nathan, even if he wants them or not. He wants them, I hope. So, and for example, MITP, Matthias had to leave because of the German strike, but also it's an amazing place in Europe. And then there are the labs, like CERN and Fermilab. Fermilab, of course, has centers that are like the Neutrino Physics Center, the CMS LHC Physics Center, the Cosmic Physics Center, and the Theory Physics Center, or Theory Division. And so they are very different in the role they have. But I think, in my opinion, and a bit agreeing with David, the physics centers have the power of doing innovative, high-impact science across many areas of physics in this particular case. And that's something that is possible because a lot of scientists from around the globe get together to a place and start discussing new ideas without being, in their box. So in some way, for me, physics centers are this, boiling pot of innovation in research. And so that's what makes them so special. The other thing that I think makes them so special is that they offer, and I think I try at Fermilab to do that, they offer to postdocs and students and young researchers the opportunity to interact broadly, much broadly that may be at a university group, with different more senior faculty interested in different areas, and therefore they have the opportunity to become much broader, to learn much more. And last but not least, I think, is the international component. So the physics centers, wherever they are, have the potential to be a glue for international science. And going into that, I would like to say that Rosario here is the president of the Latin American Association for High Energy Physics, Astrophysics, and Cosmology and Astroparticle Physics. And I think we'll hear more tomorrow. But in this hope of making institutes and associations work together, we are trying to launch an effort with Fermilab and LAA HICAP in order to do a mobility program for Latin American scientists. And I think that's all what I have to say. Thank you.
Great.
Or comments? Eduardo.
Yes.
How's the theory division changed?
Oh, theory has been changing its role, and I very much hope, but I'm a bit biased since I am the director of the division, that we have been doing it for good. Of course, we have to cope with a lot of new rules, as probably you all heard. And Director Liam Erminga and Deputy Director for Research, Bonnie Fleming, are being super helpful in helping us cope with also this situation. But let me say that Fermilab Theory Division now has 3 departments. So it's a particle physics department, astroparticle and cosmology department, and just newly founded 2 years ago, a quantum theory department. And we are really working across boundaries in 3 departments, and we are trying to become, or we are, I think, a hub for the efforts, for the experimental efforts. That would make a hub at a lab a bit different from other hubs at other places where there's just theory, less connected with experiment. So we have very strong effort in neutrino nuclear interactions, very strong efforts on neutrino big experiments, scientific work for all the LHC efforts. And newly, I think we have a very strong effort in quantum, because Fermilab also has a very strong quantum center for building quantum computers in the future. So we work on quantum sensing and quantum algorithms. So it has, if you have not been there, I invite you to come. You're a neighbor.
I haven't been there for a while.
So,
I am the director of an institute for condensed matter theory in Urbana.
well, as you know, quantum...
And we have an institute of quantum information
yeah,
science.
but quantum is at the boundaries.
Yes, I said that.
Yeah, quantum is at the boundaries, because, when you think particle physics has been, historically very connected to nuclear physics and astroparticle physics and cosmology. But now thinking about quantum science for high energy physics or for elementary particle physics, we are going a step further and thinking about AMO and material science and computer science and, of course, AI. So we are, yeah, so we are much closer. These overlapping areas is not just, as David was saying, this interdisciplinary, which maybe used to be, a buzzword from agencies many years ago. I think this is the scientific reality today.
Okay, so our next speaker is Luis Lerner from the Perimeter, one of the newest theoretical institutes.
All right, thank you. So Nathan sent me the charge of giving some thoughts about centers and institutes. I tried collecting my thoughts from the point of view of being a participant at different centers and institutes at different times, or being on the other side of the curtain, getting involved here at the board, at the KATP, and of course at Perimeter Institute. So then I tried to thought, what's a common theme among all of them that I loved and I think are very important. So if I were to define with a single word, so centers or institutes are by definition nimble. They are ready to react. They're able to advance. There is a lot less bureaucracy to help advance whatever the vision of the institute might be, whether it is hosting workshops long-term at a place like KATP, or having long-term initiative on the research side because the number of faculty is larger like at Perimeter Institute. So being nimble is there because, of course, there is the distance between the typical attendee or researcher and the decision maker, i.e. the director, is very short. I mean, at the KATP, you knew where to find David, and you just had to knock the door. And at that given afternoon, you have an answer. The answer might be no, but you had it. And at the same time, the director has a short distance to whoever is the one that is funding, and it's on the director's shoulder to try and push things forward. So I'm not going to go through all of them because many have already been said, but centers are ideal places to experiment ideas, think of initiatives, to do whatever, and then have the institute help out with maybe what makes sense is teaching relief, what makes sense is trying to do some strategic hires, or to react to opportunities. Maybe a work breaks up at the other end of the world, and then there is a number of displaced researchers. Of course, one cannot save or help them all, but there are a few one can go and interact. And it may happen Same thing in Middle East, or a crazy new president that decides to close a research funding agency in a country. It's an ideal place to take advantage of opportunities, either because a workshop made sense, because there is a funding opportunity, there is new ways of doing outreach. Again, all these different institutes will have their different visions, but in particular the one here has been instrumental, has been a unique place where workshops can take place, or schools can take place in a place that is really difficult to find funds to support these activities. So as I'm thinking with my hat as an Argentinian or as a Latin American, a center with the stability that is provided by the funding agencies that support this institute will first provide a sense of stability to the researchers in the area, to know that, well, whatever winds of change might be blowing in the particular country, there is a place where I can go and be welcome and at least help to keep my activities going, and if not myself, send my students to keep going. It's a place that by definition, because it's small, it will always be thinking beyond itself, because we know that whatever we're trying to do research-wise is much larger than we can do locally. And it's something that by definition, it will be thought as a community-owned. Everyone in the region will think of this place as their own.
Any comments, questions? If not, our next speaker is Jose Onucci, who is the director of theoretical biology, or you don't use that word, right?
Biological physics.
Biological physics. Theoretical biological physics in Houston at Rice.
Okay, so I'll tell you a little bit about our experience. I think we created the Center for Theoretical Biological Physics in 2002 with still University of California, San Diego when we did it. Was the first center that tried to explore as a center the interface between the physical science and the life sciences. So we are funded by the NSF, actually almost by an equal partnership between biology, MCB, and the physics division. And we have been at this interface for a long time. The beauty of the center is a couple things I'll tell you, is actually to work on both directions. There was the conventional biophysics idea of the world where you say, can I use what we know of physics to help to understand biology? But actually the center, from the beginning, we have put this idea that that's one way, that's one avenue. You heard some beautiful things from Bill today. But as you heard from Bill, at the same time, you can use the complex of biology to learn some new theoretical physics. So actually, the both directions is a very interesting field to explore in a sense that, I think, goes what Dave just told you before. You can use nature as a training ground for you to use the idea that a physicist think to learn in many, many ways. And if you want to talk about systems far from equilibrium, lots of information going around, that was the goal of the center, and we were sort of the pioneer on that area, or at least putting all these things together. We actually started a few years early with some funding from the Boros Wellcome Fund that was interested at that time to put some money to train people come from the physical science into that. But as people said, one of the beauty of the centers is actually a lot of the new ideas are not created by the senior faculty, but it's actually created by the postdocs and the students. So by having all these groups put together, we have basically about 13 or 14 senior investigators, but the students and postdocs share the same area. And they're all, as being part of a center, basically, you cannot run your group as a group, so there's a lot of what I call horizontal learning. These postdocs and the students talk to each other and inspiring each other, and that has been one of the great things of the new ideas coming together. And the beauty, as you come from theory, is that a lot of the tools that we use they can actually move through scales, they can actually move through problems. So in a sense, you can have someone that's doing protein folding today, and tomorrow he's working with someone doing gene networks. But if you look at the mathematics of the problem, it's very similar, and they can teach each other. So that interface of physics and biology is a very growing field. I actually think that here they call physics of life. There's a lot of new physics that's being learned from it. So I think it's important to remember this bidirectionality, and that's the message I wanted to put here. That is this thing that we can actually learn a lot from it. So we have been trying to collaborate with Nathan and see if we can do something, create in this area here in Brazil. And I think Bill has been also a partner on this game. And I want to say that people can partner, come to us in Houston anytime. Basically, we have lots of collaboration. We have visitor programs that have been very active. So you're all invited. So I think it's enough. Thank you.
Great. Any questions, comments?
So you mentioned the two directorates at NSF that are pursuing funding on this direction. I was recently at the audience of a NIH-NSF meeting, and the topic was quantum science meets biology. It was all about trying to leverage mostly physical instruments and instrumentation that explore quantum states to explore biology at a low phototoxicity level and other things. But this is, of course, on the experimental side. So do you see a movement from an agency such as NIH on the theoretical side of biological physics going on?
So there's lots of new partnerships between the NIH and NSF into this area. However, you have to understand the importance of the National Science Foundation on this problem. I actually work on quantum biology, a lot of my PhD on the time I worked with John Hopfield, I was on there. But you have to remember that the NIH is an agency with a mission. So in a sense, they're not interested in learning new physics per se. You can do it because you have some program directors a little bit more flexible and a little bit more visionary that can do it. So, so in a sense, we play the game a lot of the time. In a sense, it's basically our NSF money is very, very important because that allows us the flexibility. For a lot of the applied stuff, we can get money from the NIH, that's where we go. But you actually need the NSF money to go into the other direction. And the idea of quantum biology is actually a beautiful area these days. We know a lot about the importance of quantum effects in biology at the molecular level, but there's a lot of questions if you go to mesoscopic levels or higher levels, if you actually, quantum mechanics is important. I just want to finish this answer with one question. Linus Pauling, in the old days, used to say that quantum mechanics is important to define a chemical bond, but after that, biology is classical. So we know that's not true now, and there's a lot of interesting questions. That's a field that's basically being revitalized. There's a lot of interesting new science. There's a lot of crazy ideas, but it's actually a new area that's becoming very, very, very great these days.
Thank you. I just want you to mention a little bit about the Physics of Living Systems program that RISE leads, which I think is very interesting to mention here.
Yes, she's telling about something. I just don't have enough time to go in there, but we're also lead a program that's called the Physics of Living Systems Student Network. That's a program that started by the Physics of Living Systems program, the NSF, that involves about 8 to 10, depends how you count, institutions in the US. And the idea of this program is actually create a network of students so that we create a community for these students who work at this interface as physicists. And we have another 8 to 10 partners international then. The meetings are fantastic. The students really enjoy. When we meet together, the talks are given most by the students. There are a few faculty members who cannot resist. They want to give talk themselves, but we try to avoid that as much as we can. And it's a great area. And just out of curiosity, the meeting, we always do a meeting one time in the US, one time some other place in the country. And this year is going to be at ICTP in Trieste, since they're organizing it.
Okay, so our last speaker is Marta Lozada, who is now at NYU Abu Dhabi and will tell us about a potentially new physics institute, as much as she's able to.
Yeah, let me tell you a little bit about, say, science at NYU Abu Dhabi in general. But just to give a little bit of context, NYU had for many decades developed the concept of a global university. But it was really with President John Sexton that there was really kind of a bolder decision in terms of what would that global university be. And they came to an agreement with the government of Abu Dhabi to establish NYU Abu Dhabi. And the goal there, let's say the spark, was to think about what would it mean to develop a global liberal arts and sciences institution in Abu Dhabi. And how would you go about that? But very quickly, you know, the next step in that was to develop a world-class anchor research institution for the UAE. And so this was really what happened, kind of the birth of this institution. And it's been around for about 14 years now, really focused on having global citizens, welcoming global citizens, both in the student body and in the faculty. And within the Division of Science, again, the idea was not to replicate exactly all of the current structures that exist in Research One universities, if you want, but to be much more flexible. At the same time, focus on being in and of New York, NYU, and of Abu Dhabi, and of the world. And so the Division of Science encompasses, of course, all the natural sciences, but also math, computer science, and psychology. And now, 14 years later, we have a research ecosystem that is extremely rich, with around almost 420 research. And this is led by the PIs that are the faculty and then the research staff. But we also have additional mechanisms, which are the development of research centers. So faculty in science have developed 13 different research centers, but I only speak about 3 particularly related to physics. One is in astrophysics and space science. The other one is quantum and topological systems. And the other one in complex biological systems. And so it really is kind of the focus of what we have been working on. But we haven't stopped. We are moving on, developing more areas. Of course, theoretical high-energy physics is an area that's being developed, and we have a leading Emirati that is in this field that is part of our faculty now, Ahmed Al-Miri. You might have heard of him. And we have some other faculty joining us again in September of this year that will continue to enrich these groups in Abu Dhabi. In addition, the university has also a kind of support system structure that develops all of the public programming and all the workshops, seminars that can be used by any one of the faculty or these research centers. And so as an outcome of that, we have a real large flow of people coming in through the institution. I really invite you all to come. Some people here have been there already, and you can say, Atish, David, Marcelo, you've been there, and you can really see, I mean, from the desert, really from the desert, to what it is now. It's an amazing place. And the last thing is, thanks, Nathan, for inviting me. I don't lose my Colombian roots in this way, so thank you so much.
Thank you. Any questions, comments? Nathan.
So I have noticed that there are many Latin Americans now at your university.
How many?
There are many that I know. Yeah. So Leonardo, there are many. Have you thought about having direct collaborations with institutions in South America?
Indeed.
Okay, so we should talk.
Indeed.
So I have a curiosity. I mean, in Abu Dhabi, there are also other research centers. Is there a network or connection between NYU and these other, I think it's TII and related?
Yeah. In fact, yeah. I mean, TII is even a more recent institution that has been set up, but it's not a degree granting institution. And it's focused on very specific areas. And we do have a strong collaboration with them. And they have some, we have, David emphasized a lot of the theoretical aspects, but NYU Abu Dhabi has really set up fantastic labs as well. So we have, all the capabilities of really doing really good experimental science, but TII complements that as well. So yeah, have you been there to TII? Yeah, all right. Well, also come to NYU Abu Dhabi.
there is something I'm curious about the Abu Dhabi that we might learn from here. So here the difficulty is, I mean, of course, it's very good to attract researchers from abroad to stay for some time, but the real challenge is to grow local students to become good researchers who eventually will stay in Brazil. I mean, some of them is physiological, they will move outside, but the idea is that in some not so far remote future, in 10 years, some students might be the future generation of Brazilian researchers. So your example seems to me, I mean, I may be provocative here, kind of opposite. So you get some money from outside, or I mean, organization from outside, from New York, and you build something which is fully international. So how does it seed a local sparkle? Does it?
How does it what?
How does it see, how this revive local sparkle, I mean, a local movement of researcher?
Yeah, so, okay, so we start from the undergraduate student population. So it started being very small in the Emirati component, because most of the Emiratis that were very well trained would go abroad, right? But nowadays we have like 22% of our undergraduate student body are Emiratis. And we have already been able to show, as the cohorts have graduated, how we have also been able to then have them either continue on in our global PhD program, or go to, you know, get their more advanced degrees in top institutions around the world. We have I didn't want to focus on the educational part today in this talk, but it's a really, really, you know, fantastic outcome of the educational results that we are obtaining with all of the students, not only the Emirati students. So there is you know, a long-term plan in developing the human capacity of the local population, and they are very clear. The Emiratis plan very well. You know, similar to Singapore, they have very clear plans of what are the areas that they want to develop and invest in, and space is one of them. And there are a large number of you know, Emiratis that are more and more leading the space efforts.
I have a question that perhaps apply to the whole board, which is, in experimental facilities, we've been seeing a trend of a utilitarianism push in trying to make science as close as possible to applications. So there's this buzzword of the moment is innovation, right? And people are being pushed to set up startup companies and bring their products, research close to products. I think quantum technology is perhaps the most affected field, right? There's a spur of startups all over the world. Perhaps most of them will fail at some point, but nevertheless, they were able to capture the enthusiasm of venture capitalists. And from what you just described, I had the feeling that the theoretical physics institutes somehow have been stirred on their position and not much influenced by that. Perhaps this goes back to David's point on how much it costs to run such an institute, right? And on the experimental side, there's so much money being poured that somehow politicians and industry in general gets worried about. What's your take on it?
You know, the payoffs, the applications, immediate applications of theoretical science usually take longer, for sure. Think of quantum mechanics and how long it took before it now dominates our economy, but this was not something that Werner Heisenberg at the age of 25 could go and start a startup company on. By and large, as a theorist, I've always treasured the fact that there's no money to be made by the field that I'm in. Because although, you know, it's great for universities and scientific institutions to have this immediate payoff, we can argue for funding or make money ourselves, but it has also a corrupting influence on scientific intercommunication, transparency, and so, but more and more, as you know very well, in the quantum area or in AI, Many of our theoretical graduate students are developing skills that are immediately transferable. They don't necessarily start up companies, but they go work for companies like Google, Microsoft, IBM, et cetera, et cetera. Anyone else want to come in?
I can add a little bit to what Dave said. First of all, I think the beauty of the theory centers is that you just want to learn for the sake of learning. And you do it. But actually, a lot of the new things coming these days is based by new learning, they are new things. I think on the entire day part of data analysis, I think the physicists, because of all the training, they were prepared for it. That's why Dave said people are just going there. They're better trained here than in other places. And we all have history of now lots of our students just going directly to lots of companies that was not true a few years ago. But it's a reality today. But it's actually going beyond that. For example, we have a big collaboration with AMD where they're interested in just working together with their teams on developing new tools, on sampling data, on doing data analysis, actually doing stuff together. And they're becoming a big funding partner. But I still agree with Dave that we have to be hardcore and say we should stay honest to our mission and not try to go to the profit. Otherwise, I think it's going to make the place a little bit not so fun.
Yeah, so let me add something to that. So in our case at Perimeter Institute, this issue is simpler because the institute was started by private funding. So the guy that invented the BlackBerries was the initial donation. It was very much into the initial vision that the value of theoretical research in its own right. Of course, in the background, there were other things going where he was significantly involved, creating a center within the university that had the experimental part, creating a venture capital funding enterprise to help kind of the whole, if you want, ecosystem to go from very much theoretical developments to eventually a product. But all along, he was an advocate to say theoretical physics is important, let's keep it that way. And as part of the organization of PI, part of having an outreach component was to keep pushing that message, both, of course, to the government and to the general population to have that value be understood. Of course, we can preach to the choir and say, yes, look, we're generating these skills, and these skills eventually go to the industry. But it's really good to have someone from the other side, from the corporate world, helping you out along the way, keeping that message strong.
So, okay, so it's actually connected to what Luis said, and I was thinking of my hat as chair of the Perimeter Institute Advisory Board, that I was learning a lot about what Perimeter is doing. But before I forget, I want to say, it's not related to your question, but before I forget, I would not call theories cheap. I really don't like it, sorry. I think that we are a great investment, okay? Let me finish.
They're a great investment partly because they're cheap.
Yeah, but don't say we are cheap, for God's sake. This is a real bad way of selling us ourselves. So anyways, going. Sorry, David. No, neither inexpensive. We are worth every penny. So I think following on Luis' comments, I think that. Things have changed in the way we do science. They have changed a lot from the time when I was a postdoc, and talking to postdocs now, theory postdocs in my time basically had very little other opportunities than going into academics. And theory postdocs who are brilliant today, they have too many temptations that are really to do research at very high level, very well paid, and quite independent. But I think building the ecosystem is part of what is super relevant. I think Perimeter is an example of the things that maybe you are asking but not seeing, where I think Perimeter, no one will discuss, that is an amazing place to do innovative theoretical physics, impactful research. It's an amazing place to go into new directions and open new doors. At the same time, is an amazing place where many of the spill-offs of quantum science and AI and new ideas at high level of math are going to get into you know, venture capitals or new ideas that then are using our math and for other resources. So I think that it's not disconnected in this world today in any way, and we shouldn't let it be disconnected. So we should be, any theory institute should be part of the ecosystem around, in my opinion.
Thank you, Marcela. And the orders from above are that the session is over. Any questions to the panel should be asked offline.
So there's some things we don't control, which is traffic. So that's why we should leave certainly as soon as possible to get to places on time. So of course tomorrow we can continue discussions. So tomorrow is just for these kinds of discussions.